I used to have a bell I could ring, but I lost it. So, hello everyone. Welcome to this joint AMWG, ESPWG, CVCWG, CCWG, WAWG winter meeting. My name is Peter Lauritsen. I'm the internal co-chair for the AMWG here. In case you haven't memorized all these acronyms, I've listed them for you there. The AMWG stands for the Atmospheric Model Working Group. That's the working group that, roughly speaking, is responsible for developing the model for the troposphere and lower stratosphere, excluding chemistry and aerosols. Then we have the whole atmosphere working group that, loosely speaking, deals with the atmosphere from the upper stratosphere and up, so thermosphere, mesosphere, and all the way to geospace. And then we have the chemistry climate working group that, loosely speaking, focusing on chemistry and aerosols. These three working groups here are very model development heavy because they're responsible jointly for delivering new model versions. Then we have what I would call a more model user heavy working group. So we have the Earth System Prediction Working Group that primarily focuses on predictions beyond the typical weather scale, so S2A. An example is S2S type applications. And then we have the Climate Variability and Climate Change Working Group that spends a lot of time analyzing our simulations. Huh? There's no audio online? Okay. It's because they wanted to hear me spell out all those acronyms in one go again. So, okay, but the last working group listed here, they look a lot at our simulations, analyze them, set up new simulations, etc., to gain a better understanding of the Earth system. So this year we're trying something new. We're combining all of these five working groups for the winter meeting, and the motivation from the organizers' side here is to increase collaboration across the working groups. I think it's helpful for the model developers to know as much about the model users, know what's working in the model, what biases are in the way for you to do your science. And then the other way around, I would argue it's good for the model users to know what's going on in model development and why did we take certain decisions and so on. We also thought it would be a great opportunity to have joint discussion on our model, or our new model performance. We are a community modeling system, so we're always looking for input from the community, both in terms of model development, but also experiment design. Last but not least is also to reduce meeting load, because these working group meetings are usually spread over several weeks. So if you were to attend all of them, you have to set a time much more time that you have to do in this case, where we'll be done in about 3.5 days. Okay, the structure of the meeting here is we'll start out with the model development heavy working group. So just briefly go over what's new in our latest version of the model. Then we're going to have some presentations on the performance of our model. We also have to take into account that certain people are not, or certain speakers are not available all the time. So we sprinkled in Natalie here in between these. And then at the very end here, the last session, we're going to focus on specific features of the model. And if you would like to join, there's like an informal happy hour at the Southern Sun, so it's a brewery right down the hill. We're going to continue the joint sessions tomorrow, so then we're going to have a model user heavy working group present what's going on. So we have the climate variability and change updates and associated talks, and then we're going to jump into prediction related talks to end the morning. And then in the afternoon, we have a session on high resolution applications within the CESM. And then we have the rest of the afternoon dedicated to machine learning applications, either using CESM or putting in machine learning parameterizations into CESM. So that's the end of the joint working groups. So then on Wednesday, we split out. I call them less joint working groups because there's still stuff that is joint, just not all of us together. So ESPWC will stay in this room the whole day to do their joint sessions. The AMWG will be in the Damon room. And then the chemistry climate working groups and the whole atmosphere working groups will start Wednesday PM and run all the way into Thursday AM. For those who are interested, we also have a club tutorial in the Chapman room Wednesday afternoon. And then we've converted one of the abstracts here into a full seminar. So if you can, please come to the CDD seminar on Thursday at 11. So that's all I had to say on behalf of the organizers. Now I'm going to put my AMWG co-chair hat on and very briefly go over what's new in CAM 7. And I'm assuming that you lived under a rock since CAM 6 was released. So if I had to put just in one slide what is new, this is what I would put up there. So a major change from CAM 6 is we have raised the lid of the model to have a well-resolved stratosphere. We've increased the resolution in the boundary layer. After several decades using the finite volume dynamical core, we have switched to a more modern dynamical core, and we also have non-hydrostatic dicore option in there. We've kept advancing our boundary layer and microphysics schemes. So for those of you who are familiar, it's Club and Pumas. We've adopted new parameterizations to represent missing processes in the model. We have reordered the physics time loop to deal with spurious oscillations in the boundary layer and the winds. We've taken major steps on the CAM physics side to move towards generalized thermodynamics. That's both. That has to do with species-dependent air. We're continuously expanding our simpler models effort. And then the last points here are less sciencey, but I believe they're really, really important. We are constantly improving our code base and trying to reduce scope of the system. And we have a much improved workflow, both in terms of simulation tracking, diagnostics, and interacting with our software development team. And the last bullet here is everything I didn't mention. So I have a slide on each of these that are in blue font. So first of all, the change of model top. So on the left-hand side, you see the level thickness in meters and pressure on the vertical axes. The hollow black circles is our old model version. So it had a top at 40 kilometers. We put together a vertical resolution task force led by Ayla Simpson a while ago to figure out what the resolution should be throughout the stratosphere to represent the phenomena of interest, and we ended up with the red dots here. So that's what we call the mid-top model. We roughly 3x'd the number of vertical levels. So this model is 3x more expensive just in terms of the vertical levels. So we're still maintaining a low top version to have a cheaper version of the models. That's what you see in the blue dots there. That's referred to as the LT model, the low top model. As I mentioned, we have also moved to a different dynamical core. So for our mainstream applications in CESM, so I'm talking about the 1 degree IPCC class model, we've adopted what's called the spectral element dynamical core is defined on this mnemonic cube sphere grid. There's a lot of details about this dicore I won't go into, but like it allows for the separation of the dynamics and physics grid. This dicore, as opposed to our previous dicore, is highly scalable. We have more advanced thermodynamics in there. It allows for mesh refinement, which is relatively popular, and it has pretty good conservation properties, and not just mass, but also angular momentum. Also, we have more and more really high resolution applications of CAM. So we now have the model for prediction across scales. So the MPAS dynamical core is now in CAM. And I call that a sustainable implementation because we're pulling the code as an external from the repo where the developers have the model, and the main developers are here at NCAR in M-Cubed. This DICOR is being heavily used in the Earthworks project, for which we have a presentation tomorrow, and also in NCAR's SPAD initiative that we also have a presentation on later on. For those of you who like geospace modeling, you should be pretty excited because there's work going on making this a deep atmosphere model. And there's also a GPU version of this DICOR. All of this is in CAM. You can check it out from CAM. The other project here is not in CAM at this point in time. The project started fairly recently, but this is to bring in DOE's non-hydrostatic dynamical core into CESM. That project is called Storm Speed. This DICOR has the same origins as the NCAR spectral element version. They also implemented a separate physics grid capability that we're using here. But it's non-hydrostatic. It has a really ultra-fast similar Lagrangian transport scheme in there. It has a different programming paradigm than our existing DICORs. It's coded in C++ and has COCO support for GPUs. And for those of you who run variable resolution application, know that we do not support this separate physics grid and faster transport scheme in the NCAR version of spectral element, but the DOE version does support that, which will speed up the model quite significantly. CAM7 has also new parameterizations in there. So Meg Fowler will talk a little bit about this, but she put in together with Rich Neal convective gustiness parameterization. Julio Bachmeister and Martina have been working on a missing, what we believe is a missing source of gravity waves in the model, referred to as moving mountains parameterization. Julio will talk about that later. Then we also switched to a more accurate dust emission scheme that Danny is going to talk about. So now on to what I've alluded to, like less sciencey side of the story, but really, really important in my opinion is the workflow around the model. So Cecile Henne has been working really hard at a GitHub workflow for our simulation. So that's this repo called AMWG_dev. There's also one for CESM. So the AMWG one, we mainly track AMIB runs. The CSM one is coupled runs, but in here you will have a very complete description of what is being run, a discussion, if applicable, to it. And then associated with that, we have this ADF, a diagnostic framework written in Python. So we run diagnostics on all of these simulations. And there's much happening in the diagnostics world here. You can hook the ADF up with other diagnostic suites, and it's been integrated into what's called the QPIT workflow. And we're pretty close to the situation where you can run CAM, and then it would automatically also do the ADF diagnostics once the run is done, which I think is pretty cool to have that workflow. Also, in terms of the interaction between software engineers and science, everything again is handled on GitHub. We track all the PRs and so on. I think everybody does that, but what I want to emphasize that we have like bi-weekly or weekly meetings where we with the scientists prioritize what's going to happen, what's going to go into the model next, etc. And that has really helped accelerate development. Looks like I accidentally removed one of my slides here. But one thing I do want to mention, so our current code base is sitting under ESComp on GitHub called CAM development, but I also want to make people aware that we're working on a separate code base with expanded scope. So that's called CAM SEMA. So in here, we're compliant with the CCWG protocol in terms of bringing in parameterization. So that will make it easier to move parameterizations around between CCWG compliant models, but we're also doing a lot of modernization of the CAM development software. So in terms of the unit testing software in terms of handling constituents that have like an automatic way of dealing with in terms of a constituents object in there. I forget the third thing I wanted to mention here, but it will probably come to me. But I just want to make people know that we have this modernization going on of our work, of our main scientific code base. The other thing I wanted to mention is that we have both the spectral element dicore in there, we have the MPAS dicore in there. We also have plans to bring in the WAR physics suite in there to be able to run that physics suite within this modeling system. So that's an expansion of scope. Alrighty, last but not least, I also like to just advertise that we have spent quite a few CPU hours running high resolution simulations of a quasi-final version of CAM7. So we've been running quarter-degree runs, all F cases, all 10-year runs. If you click on that link there, it will bring you to a full description of the different runs. So we've been running the mid-top model, that's the L93, the low-top L58, and then also the old CAM6 vertical resolution, the L32. And we've done some sensitivity tests here related to our boundary layer scheme. And we've also run, standard SST and then SST plus 4K experiments as well. So if you're interested in these simulations, really hope that people would like to dig into them and have a look. You can contact Cecile Hannay. Since we don't have a specific talk about this, Ben will talk a little bit about it. I've just thrown in this slide here. If you look at the tropical cyclone tracks observations versus our quarter-degree run here, we're getting pretty encouraging results there. We got improvements in the stratospheric polar night vortex. But as usual, not everything improves. We're seeing some degradation in the double ITZZ in particular and in the monsoon. So that is all I have. I can entertain a quick question if we had that. Otherwise, we'll move on to the chemistry climate working group update. No questions. All right.
How hard is it or not you finding to tune the quarter-degree?
We haven't really attempted to tune it. We can run with 1 degree settings out of the box. It's always a challenge because it's very expensive, so you can't do 110-year simulations very easily. Julia, did you want to add to that?
I was just going to say that the challenge is tuning it in a way that improves the seasonal means and also preserves mesoscale variability.
Go ahead. Following up on this, so what's the strategy, how to tune it?
The quarter-degree? I'm not sure what our strategy is yet. I hope we'll be able to set up much shorter simulations. But right now, we're pretty overwhelmed with getting the 1 degree model ready. I haven't spent too much effort on it yet. Hearing a slight echo, so somebody has audio on their laptop. Okay.
Hey, does that work?
Fine. Yeah. Okay, great. Okay, welcome. This is the Chemistry Climate Working Group talk and overview what's new. I'm the co-chair together with Rafa Fernandez, and we have our liaisons, Rebecca and Sean here in the audience, and Francis, that is our software engineers. I also thank you for contributions of various other people, also Louisa, Doug, and Ben, and specifically. I want to start talking about chemistry, what's our chemistry, since this is chemistry climate talk, to remind people about what chemistry do we have in the model, and also about new acronyms that we are using now. So it's like coming back. People may remember the WACCM model, CMIP6. The chemistry was called TSMLT, troposphere, stratosphere, mesosphere, lower thermosphere. Now we are changing the acronyms in some way. For the troposphere, we'll have like the T, but we have different chemical mechanisms. So the T1 is the one that has been used like for the TSMLT, the standard version. And then we have different numbers for different complexity of those mechanisms. If you can see on the left, they are the components of the chemical mechanisms. On the left is the TSMLT, what we now call actually then the T1MA, which we do for stratosphere, mesosphere, lower thermosphere, call it middle atmosphere. But for the mid-top model, we'll call it T1S because it doesn't have the upper part. So you can see that the there's a typo still, the T1S in the mechanism has quite a few components, and that's what we use. But we wanted a little cheaper model, so we developed a model that is now the T4 tropospheric mechanism that has quite a few reduced chemical species, reduced hydrocarbons, and so we actually can reduce the model costs by more than 30% with that. And that is quite helpful when we run the long climate simulations. It isn't that suited for air quality, or we'll talk about it later. But then this model is certainly the advanced model for the workhorse model. And then we have the specified oxidant models, which is really the chem model that you're used to, the simple chemistry. And so here's just showing you can use all these different chemistries in the different configuration. Like in WACCM, you can match and mix. You can only run middle atmosphere without the comprehensive troposphere chemistry. We have different mechanisms that are more complex, and I will talk a little bit about the halogen chemistry. So what we do for the workhorse model, as I said, is the T4S. So now you kind of have an idea what that means, the T4S chemistry. And we do use that also to do several model simulations and to produce oxidants and other fields that are required to actually run chem. And all of these chemistry that are in the gray can also run in the 93 level version, as well as the 58 level, the low top version. And so where are we with our planning for the experiments? As I said, we use this mid-top model, the T4S chemistry. We use the model, the MAM5 aerosol scheme, which is comprehensive in having interactive aerosols as well as chemistry, including volcanoes. As I said, we produce the oxidants for the chem runs, and this is really required. This model is required for airchem MIP, geomip simulations, and probably other MIPs like CCMI and HTAP and so on. And so we're also planning a tier 2 kind of experiment set. Because not all the developments have yet been included that we wanted. I come to it in the next slide for the chemistry group. But also, we want to have something that focuses more on air quality and greenhouse gases. And so that will also be a baseline for more detailed chemistry climate studies. And those runs will be discussed in later working group discussions. So what do we actually include? There's a whole list of also bug fixes I didn't add here or other updates, but the general thing is the new chemistry, the model aerosol scheme is updated. And then we have the new dust from Danny that is included. We have online BMS emissions that are based on a machine learning approach. But there are things that are not included in the first simulations, which is the new photolysis scheme that Doug and June are working on. We do not have this short-lived halogens emission and chemistry yet in the workhorse model or in the CSM3 version, and updated soil NOx emissions. And we hope that we can by summer make some progress here and then also construct new updated simulations. We do have computer time that we reserve for that. Other things are in development that we are still continuing that will not be in the CMIP7 versions likely, like also a new aerosol scheme that we are working on, and you will hear about the KAMA sectional aerosol model for aerosols as well as for clouds, nitrate implementations, and also the HEMCO emission tool that is processing emissions online while it is available for the users in CSM3. So then we are in progress of producing model simulations with our new T4S mid-top run. So far we have done historical simulation with fixed SSTs. And I show some results in a little bit, and there's more detail later in the working group meeting with WACCM and ChemChem. We also working on the new forcings for CMIP7, and in particular, we're working on a new volcanic forcing data set on surface emissions, solar forcings, lower boundary conditions, and Doug Kinnison is heavily involved in running also a WACCM 2-degree model right now to test these new emissions, but also to reduce forcings for other models for ozone and so on. And Ben Gabier will give a talk on that later on as well. So the new forcings will be produced and then run in the model version. And we also will work on our model, on the T4S model, to produce forcings for our CHEM model, for the simplified model, which may change also radiative forcings and other things. So the next steps will be to run an 1850 model simulation, produce new forcings for the specified oxygen model runs, and then see if radiative forcing changes. So we can start our work on an interactive chemistry model towards, more simpler chemistry to tune up the model and so on. Then we eventually do test simulations. So I want to give a few highlights from our T4S simulation. And also, this is just one example for the new CMIP database, like the volcanic SO2 emission database, just to show a little bit of the challenges that are going to come. There is a new database. They call it now the CMIP 6+, which will be eventually CMIP 7. It has new injection, height variability. It has eruption locations that have a little changed. I mean, they have updated them. Missing volcanoes are included, satellite era improvements. And that's one thing that you can see here, for example. There's a lot of more volcanoes in the satellite era. And people saying, wait a minute, that can cause some problems, because here in the previous time frame, we also had these small volcanoes. We just didn't include them because they weren't observed in the ice cores. So what is happening now actually today, we got a new data set where these are extended. And so we want to keep the forcing very steadily between the whole pre-industrial towards the present day, during the historical period. So there will be a new database that may increase the forcing of the volcanoes. So we have to test that as soon as this is available, and it seems like it is available up to today. We just did some test runs. We have to be careful because the new CMIP data set is not necessarily suited everywhere for our model. What you can see is that in general, the AOD, the stratospheric AOD of the model, is reproduced when we use the CMIP 6 database that we use for Mike Mills. If we use the new CMIP7 database, we get an overestimation of Mount Pinatubo. But as in Mike Mills' data set, we kind of scale the model for large volcanoes because we know that the model has a specific feature to overdo it. So we comprehend that way, and we know that that's helping. So we cannot, we'll have to adjust for it and give some more updates in the summer. The other performance a little bit now, so we do look at AOD for the troposphere as well. We have the new dust scheme, which we have implemented. We also had changes to the land model, and more people from Dave or others from the land model can maybe help out here if there are questions. But changes in the dust model, this is the old dust here on the right, AOD, from the model minus MODIS data. We had some hotspots, too much AOD over the southern hemisphere, Australia, I go back South America. This has been greatly improved. But we also get a little bit low bias now in higher latitudes, and we're still figuring out what happened. And it could be that the land is just not producing enough secondary organic aerosol precursors, and this could lead to some of the underestimation. We did look at aircraft data. The ATOM aircraft data set is a great way to compare the model. So this is a data set that we had data between 2016 and 18 that flew over the Pacific and Atlantic over 4 years for different seasons. And this is kind of a climatological comparison, and so not really on the flight track. But you can see that, for example, for extinction, on the left here, we see the ATOM data, on the right, the model. It doesn't look very bad. I think it looks pretty good. We do see somewhat an underestimation over the specific region in the Northern Hemisphere compared to the data. Comparing this to organic aerosols, for example, we can also see that underestimation. So there's some hints that we are underestimation, but there could be other things that we'll still have to explore. So this is work in progress. Other things to point out, we are happy about the tape recorder. This is the climatological zonal mean seasonal cycle of water vapor in the tropical belt. And you can see that the tape recorder is usually showing a dry phase and then wet phases with a certain slope in the atmosphere. This is MLS in era 5. Even these data are not, the same, but our model is doing a pretty good job to represent the dry and the wet phases, although as there's always, and we haven't solved that problem yet, a maximum in April, May that shouldn't be there, or it's not in the data, that we still have to figure out why that is. Other things, and thank you, Doug, for doing last minute analysis on the run for the total column ozone. We had an earlier run where we were really excited. And now we have the latest beta 4 tag, moving mountain tuning and other things we will hear about. But our ozone, total column ozone for the October Southern Hemisphere looks fairly good. The evolution is great. It's a little cold maybe, but we're not too unhappy about it. Sorry, for the Northern Hemisphere march, however, we'll just realize that we are probably still having some problems. The ozone values are too low. That means too much ozone depletion. Doug had looked into it a little bit more with too much denitrification in March, meaning that we're probably not getting the southern stratospheric warmings correct. We have to look into this, but this is where we are. We're tuning the model, and so we're testing. Very quickly, and I'm not going into the details, this is a Taylor diagrams of comparing the T4S and T1S mid-top model. Basically, you see the blue points and the red points on top of each other comparing to ozone zone data. They are performing all pretty well, so we are happy with that. We don't see anything that would raise any alarms at this point anymore. And so I think I have 5 more minutes. I do a few more updates. And well, then I don't have questions, but maybe quickly. So I talked about the short-lived halogens, and this is a slide from Rafa. And so Rafa and Alfonso's group is really working on updating this. We have more interactive emissions, and the chemistry is improved in the model, which really leads to an improvement of the atmospheric oxidation capacity. And that also leads to improved greenhouse gases, very short-lived halogens, as well as CSCs will improve that way. And when you change the oxidation capacities, if you run interactive methane, you also change that. So that's why we want to actually do our tier 2 comparisons. There's more on this work coming in the other later on this week. Ben Gobert has a study on actually interactive methane that we're also doing. He has interactive methane simulations, and he combined that with the short-lived halogen chemistry and can clearly show that adding short-lived halogens is improving the model in terms of methane concentrations. The black line is satellite observations, and the dashed lines are the very short-lived halogen simulations, while the previous simulations without that chemistry shown here. So we really have an improvement, and we can also match CO much better. That is a long-term problem that we had in the model. We also do a lot of work still on our on our multi-scale infrastructure for chemistry and aerosols. A lot of people in ACOM and also in the community use ChemChem with spectral element. And this is the Musica version 0 model that we are using with various applications and science questions as listed here. We're also using the MPAS dynamical core for looking at really up to 1 kilometer resolution with chemistry, which is quite exciting. So you see all these studies, and hopefully we hear later more about those. And I do want to point out that we're working on the ADF chemistry as well. So we worked a lot with Jesse and Justin on improving the ADF, or actually having chemistry evaluations right there. Like what I showed, some of these plots are actually integrated already and people can use them. I do have 2 more slides on some Chem 6 physics development, but I think I skipped them now and rather have time for some questions. Thank you.
Are you planning to run CSM or like the CVCWG version with interactive atmospheric methane?
That we have to discuss what we do for that here too, or whatever, right? For that version that we want to run with the BSL chemistry and with the improved chemistry mechanism. If we want to run with interactive methane, it would be great, I think, to do that. So we'll still have to figure out the details. Thanks.
Yeah, you showed the total column ozone plots, and you showed the northern hemisphere. It's biased cold, which is potentially due to the sudden stratospheric warming issue. In the southern hemisphere, it's biased cold, and that also includes the moving mountain parameterization, right? So it looks like there might be some more gravity wave deposition that needs to happen in this version of the model before we get the temperatures right. Maybe Martina will talk about that later.
We already shared the run with Martina. We just hadn't the chance to look at it. So yeah, we're hoping that we can fix that. And Martina and Dynamics.
All right. Let's move up in the atmosphere with the whole atmosphere thing. Everybody's using a different format here. Wait,
You can come in. Fine, okay. Okay, so yeah, I will give the whole atmosphere working group update, and this is on behalf of myself and Martina, the internal co-chairs. Danielle is the external co-chair, and Mei Zhang is the liaison, and of course everyone else who has contributed to WACCM and WACCM-X development. So just as first a brief overview of kind of where we are going with WACCM and WACCM-X for CSM3 and comparison to WACCM and WACCM-X for CSM2. So the main change is the adoption of the spectral element dynamical core, as Peter already discussed. So we will adopt that for both WACCM and WACCM-X, which especially for WACCM-X involves a lot of additional development to extend it into the thermosphere. And we would like to run with both a 1 degree and 2 degree resolutions. And then there is an update in terms of the vertical levels. So WACCM 7 will have 135 levels as opposed to 70 levels for WACCM 6. And then the chemistry is also updated as was just discussed. And then also we will use the CAM 7 to 6. And the priority development objectives for WACCM and WACCM-X are essentially to have a good QBO at both 1 and 2 degree resolution, and also get a good seasonal cycle of both dynamics and the chemistry. And then we wanted to extend the SE dynamical core into the thermosphere, and then also get the climatology right for the upper atmosphere. So some of the recent development and updates for both WACCM and WACCM-X. I will discuss the ones in bold and just briefly discuss the ones not in bold. So first, the tuning of the QBO has been a main focus of the past few years for WACCM 7. We have tested the updated chemical mechanisms that Simone just discussed with the T1 MA and also T4 MA. So those have been tested in the WACCM 6 just to make sure that they're set up and working correctly. Another issue that has been a sort of focus for the development is getting the model to run stably at a 1 degree resolution. So frequently when we run at 1 degree, it goes unstable and will crash. So trying to get it stable so that we can run it with a sort of lower dynamical time step and get good throughput has been a significant focus as well. And then we've done some benchmark simulations for kind of evaluation and future tuning. And I'll go into the QBO and these sort of benchmark simulations in a bit more detail. For WACCM-X, a big focus was the extension of the dynamical core into the thermosphere. And last year, Hanli, I think, presented a whole presentation on this, so we won't repeat that here. More recently, we've updated some of the chemistry in the mesosphere and thermosphere, and then the high resolution capability, including nudging to reanalysis to recreate sort of realistic weather events at high resolution in WACCM-X. So first, talking into more detail about the QBO. These are the kind of old simulations just to show you where things looked about 18 months ago in the spectral element dynamical core on the left, and then the right, the old sort of finite volume with 110 levels, it could resolve a QBO. And if you look here, the QBO in the new version of the model was much weaker, and the maximum amplitude was quite a bit higher than you got in WACCM 6. So this is where things looked about 18 months ago. And then I'm not going to go into all the details here, but a significant amount of tuning and a lot more tuning, and then I think more tuning. That if you really want the detail, Mejong will present this on Thursday morning. I'm not going to go into everything that's been done, but as you can see, these are all different experiments looking at changing different parameters in the model and try to get as good as possible for the QBO. And I should say it's been significantly harder to tune this compared to WACCM 6. So in WACCM 6, it was, I don't know if straightforward is the right word, but it could be tuned relatively easily. But in WACCM 7, we've had to run many more experiments to try to get something that is looking a bit more reasonable. And Mejong, again, will present this Thursday morning if you want to see the sort of finer details of that. But this is where things look in a sort of more recent simulations. So the top here is WACCM 7 at 2 degrees, and then here is mid-top cam at 1 degree. And you can see both look reasonably like they're getting a QBO. And here on the right is just looking at the amplitude on the bottom right, and then the period in the upper right. The red is WACCM, and the blue is CAM. And in general, CAM has a bit of stronger amplitude, but a little bit slower of QBO. And we're hoping that we can kind of tune this one, that basically you could get a stronger amplitude and speed the QBO up a little bit. And now we have a bit of room for tuning. So hopefully we're finally getting close after 18 months or 2 years to get a QBO that is looking reasonable. So hopefully by the summer, we may have a QBO that is finally looking good in WACCM 7. And then looking a bit at some of the other climatology in WACCM 7, this is just plots comparing sort of Northern Hemisphere winter climatology of WACCM 6 simulations on the left, and then the right is WACCM 7. And by eye, you can see they look relatively similar. This isn't a sort of fully tuned version of WACCM 7, but it looks quite close to what we had before. And then the differences with respect to MIRA are on the bottom. And you can see, although there are some differences between the two, they're relatively close. So we're sort of, with a little bit of fine tuning, we should be close to what we had in WACCM 6. And here is just comparing at higher altitudes to SABRE temperature observations. And again, the sort of biases in the model are quite similar to what we had before in WACCM 6. So we should be in a relatively good position to sort of, with a little bit of extra tuning, get to where we were in the previous model and have additional new features as well. So looking at the vortex variability, this is Northern Hemisphere. So on the left here is comparison between sort of climatology in WACCM 7 versus ERA 5 for the winds, and they look not perfect, but generally reasonable in the sort of latest development version. And the right is distribution of the stratosphere sudden warmings in WACCM 7 and ERA 5. One thing to note, this is kind of total number of SSW. So the ERA 5 is about 40 years, and then WACCM 7 is only 20 years. So you kind of have to divide ERA 5 by 2 to get roughly something similar, and that's where these extra lines are. And you can see generally the distribution looks reasonable, what we have so far for this short run. The one issue is we still get these sudden warmings in November in WACCM 7, and this was an issue in WACCM 6 as well, but it's still sort of showing up in the latest version. But otherwise, the seasonal distribution looks good so far, but this is a relatively short run to kind of determine the full statistics off of. And last, in terms of WACCM, is looking at the Southern Hemisphere polar vortex. This is an earlier version run without the sort of latest gravity wave parameterization. So we might expect, hopefully, improvement in the future. But here you can see the bias in terms of seasonal cycle in the stratosphere is quite large in WACCM 7, kind of up to almost 15 Kelvin, whereas in WACCM 6, it was about half of that. So right now, the bias is much larger, and we're hoping that the sort of new gravity wave parameterization will help address this bias, especially because this has a big impact on the ozone variability in the Southern Hemisphere. So moving on to kind of the more WACCM X focused updates. We've done some chemistry updates to the model, which are shown in this table here. Some of it was just updating reactions to sort of address some deficiencies, which I'll go into a little bit. And then we added in new reactions, and this is to make WACCM X chemistry more consistent with the chemistry which was in other high altitude models, TIE GCM and time GCM. So now we have sort of consistent chemistry in all of the ionosphere, thermosphere focused models. And here is just a bit more discussion on this one reaction rate that we spent a bit of time making sure it was right. So the old sort of CSM2 rate was this JPL 17 rate, which is the grayer line here. And then the updated rate was the blue line here, which was JPL 19. And you can see at the high temperatures here, it significantly reduced this the reaction rate, and that created less nitric oxide in the thermosphere. And so we updated this based on laboratory observation and a 3-parameter fit, which is the red line here. And this reaction rate has a significant impact on the sort of thermospheric temperatures because nitric oxide acts as a sort of cooler. So then if we have too much or too little, we basically get the temperature incorrectly. So by updating this rate, we should get a better temperature, and then that also impacts the neutral densities as well. And here is just to look at how much of an impact the change in chemistry has. So the left, this is just a 10-day average of the neutral density in the thermosphere. The black line is an old chemistry, and then the red dashed line is the new chemistry. And you can see there's about 20% sort of reduction in the thermosphere neutral density with this chemistry update. And the right is showing different model simulations of different models, but focus mostly on the green line here, which is WACCM with the updated chemistry compared to the black line, which is the observation. And you can see generally we track the observation quite well now with the sort of updated chemistry. And you can see if we had a sort of 20% larger, we would be sort of too high relative to the observation. So we think that these updated rates are giving us better thermosphere climatology and more consistent with the observations. And then the last thing in terms of WACCM is the ability to do sort of constrained high resolution simulations. So recently we implemented the kind of physics side nudging for the high resolution WACCM. So now we can run quarter degree simulations with sort of constrained dynamics in the lower atmosphere so that we can recreate the day-to-day variability and look at the kind of small scale impacts and how they impact upper atmosphere. And here is an example showing this capability. So this is a gravity waves during the Hurricane Helene. And this is from the NASA all satellite mission, observing basically radiance of the gravity waves around 87 kilometers. And you can see these sort of concentric waves, at least part of the wave, this sort of concentric wave signature that you would get from a sort of gravity wave propagating up into the mesosphere. And then here is the high resolution simulations. And you can see these sort of concentric gravity waves when the hurricane is sort of impacting Florida at this time. So we can sort of match relatively well what we see in the observation. And then these waves also then eventually propagate all the way up into the sort of thermosphere, ionosphere. And I'll give more details on this capability on Thursday morning as well. And then last, we did recently have a community survey to get a sense of what are the science use cases for WACCM and also WACCM. And they're quite broad, as you would expect from models that extend throughout the whole atmosphere. And there's a huge range of use cases. This is a word cloud from what people said they were using the model for. And if you look in detail, it's kind of spanned a whole range of different science. One thing that we think came out of this is historically WACCM was kind of a focus for people doing stratosphere science. They mostly used the WACCM model, but now with the mid-top cam, that overlaps a lot in terms of what is sort of science capability for doing stratosphere science. So usage of sort of cam mid-top versus WACCM for doing stratospheric science needs to be clarified. And we're hoping to do some more analysis and then sort of give some guidance to community in terms of when they should be using which model, specifically, especially for stratospheric science. And Martina will give more details on the sort of results of this survey on Thursday. So if you're interested, please join that. And we would hope to have some discussion surrounding this as well. And then just to sort of summarize and give us a sense of what's remaining, the tuning of the QBO has been, as I said, a significant challenge for WACCM 7, but I think we're getting hopefully closer, and we'll get something that looks reasonably good here soon. And there's this large cold bias still in the southern hemisphere stratosphere in the sort of previous model version. Hopefully with this updated gravity wave parameterization, that will help to sort of address this, and it will go away. But at least as it stands now, that's a bit of a concern. And then the throughput and cost are still an issue for the sort of 1 degree WACCM model. And this is largely due to this sort of occasional instabilities. So hopefully if we can address this, we can get the model that's a bit faster and we can run more consistently. And then the last thing is we still need to do some kind of benchmarking simulations for WACCM with the new sort of physics and chemistry so that we can evaluate the climatology. And so I will stop there and can take any questions.
So here's the clarification. So is it not using any of the moving mountain parameterization at all? It's kind of adding that in would be what you hope would fix it, or it's the updates to it?
It's adding it in. So that run did not have any.
Okay.
Two things. One is, can you explain what the source of these instabilities are? And
In a 1 degree version.
yeah,
I think it is, Peter maybe knows more, or Meijiang, but my understanding is basically just dynamical instabilities. That you're resolving maybe more waves in the 1 degree that get very large amplitude at the top of the model, and then they just go, it creates the model to go unstable. And it's not a regular occurrence, but it's every few months, you will get this sort of really large wind amplitude near the top of the model, and then it will crash.
Yeah, the problem is gravity waves grow exponentially with height, unfortunately. A lot of modeling systems model developers have been talking to, they're all struggling as soon as the top is over 140 kilometers or higher. So it's a real challenge.
then the second question was on the tuning of the QBO being such a challenge. Is that, so can you explain like why it's so hard to tune the QBO because of the length of simulations, and is there any promise to develop something that's more automated, using machine learning or these other techniques?
I think one of the challenges as soon as we switch from basically to CAM7 physics for reasons not fully understood, the model tuning didn't behave the same way as in with CAM6 physics. So if we ran the model with the SE Dyncore and CAM6 physics, you could probably tune a QBO just fine. But some update in the physics makes it not behave quite the same way. And in terms of automating it, we haven't really discussed too much of it. There's something you can do to speed it up and not have to just manually sort of tune all the parameters.
I just comment on it. So from my understanding, Dave, a lot of it has to do with the changes in the depth of convection. So with the changes, once you put the boundary levels in, so then it completely changes so the distribution of wave phase speeds goes with the depth of the convection, which is much shallower than in any previous version. So then it also gives you a very different distribution of wave phase speed. So it's a completely different system.
So if any of the tuning in the CAM physics in the last minute affects the depth
All
of
of it.
convection, it's all going to affect the QBO.
Yeah.
Okay, I'm amazed we're like right on time in a second. That was the updates from the, what I call it, model development heavy working groups. Now we're going to switch to elevating the model. Please have empathy for Isla. Our machines were down all weekend, so the diagnostics are very fresh.
Thanks. So this is going to be a bit of a mishmash of things in the latest development runs, kind of how it's looking in terms of aspects of the large scale climate. Okay. So this is going to be looking at the 121 series of simulations. So these are the latest simulations that we have a decent amount of years for. So we have a 200-year-long pre-industrial control with this configuration. And we have one historical member that started from year 75 And then thanks to Cecile running some things on a kind of rapid timeline, we also have a 1% CO2 simulation that started from year 125. And we also have an abrupt 4 times CO2 simulation that also started from year 125. So I just want to emphasize this doesn't represent the final state of the model. I'm going to point out some things that are not looking so good. Rather, it's kind of the current state and maybe some things we need to focus on in the next round of tuning. And so I'm going to compare with the CSM2 large ensemble, the first 50 members, because we're currently running without the smooth biomass burning. And so that's equivalent to the first 50 members. In some aspects, I'll compare with CMIP6, and then I'll also be comparing with observation-based data. So let's start with the global mean surface temperature evolution. So this is the observed global mean surface temperature anomalies relative to 1850 to 1880. Here I'm using this recent descent observation-based surface temperature data set, and this is a 200-member ensemble, so you have an uncertainty range that kind of reflects the uncertainty in the observational record. And so that's what it looks like in observations. This is what CSM2 looked like. There's maybe some hints that we weren't warming enough over the kind of first 3 quarters of the 20th century. And then this is what the latest CSM3 development run looks like. So it looks pretty good. We do have a kind of very rapid warming. This is not gonna, see if I can use this here. Did that work? Okay. Yeah, it showed up on there, but okay, I'm gonna not use it. But that kind of rapid warming is probably due to the biomass burning emission. So we'll see that might kind of go away when we use the smooth ones. We have a short pre-industrial control, so there's still some drift going on. This dotted line here is what you get if you remove the equivalent time of the pre-industrial control. Can't do that for the whole simulation because the pre-industrial control is too short. But I think the point here is that that's not really impacting on our evolution over the 20th century. Here on the left is the land surface temperature, and on the right is the ocean. So that's observations again. Here's what CSM2 looked like. And when you look at the land, it's pretty clear that it was not warming enough over kind of the first 3 quarters of the 20th century. And then this is what the CSM3 development run looks like. And it looks a lot better over the land over the 20th century, with more warming happening kind of over the first 3 quarters than what was happening in CSM2. And we don't know for sure, but most likely this is related to changes in how the aerosol effects are behaving. We had a pretty strong aerosol radiative forcing in CSM2, and it's weaker in CSM3, although we don't have that number for this particular version of CSM3, but that's what we had for an older version. So now I'll show you the climate sensitivity and the transient climate response. And so what you see here is equilibrium climate sensitivity on the y-axis and transient climate response on the x-axis. All these gray dots here are all of the different CMIP6 models, so there's a correlation between these quantities. This is what CSM1 looked like. So it was kind of, that wasn't a CMIP6 model, it was a CMIP5 model, but it's kind of in the middle of the pack compared to these CMIP6 models. And then, of course, this is what the model that was CSM2. And so our equilibrium climate sensitivity was much higher in CSM2 than it was in CSM1, but the transient climate response didn't really change. Here's the CSM2 2-degree model. And the reason I'm showing that is that Zhang Zhu did a lot of work with this configuration for paleoclimate studies and showed that he couldn't reproduce the last glacial maximum with the CSM2 2-degree configuration. And he did fixed a few things and changed some things in the microphysics and produced this paleo-calibrated version of CSM2, which had a much lower equilibrium climate sensitivity and was able to reproduce the last glacial maximum. So I think from various lines of evidence and in particular this paleo work, we kind of think that the equilibrium climate sensitivity in CSM2 was too high. So here's what it looks like now, thanks to Cecile giving me the numbers this morning in the CSM3 development run. So the equilibrium climate sensitivity is back down to kind of near where CSM1 and the paleo-calibrated version of CSM2 is. A little surprisingly, the transient climate response is lower than any of these previous versions, and I don't think we had seen that in other development runs, so I think it remains to be seen whether that continues. And so this is all consistent with the model also working well for the last glacial maximum. So this is a figure from Zhang showing last glacial maximum global mean temperature on the left and top of atmosphere radiative imbalance on the right. And so the problem in CSM2 was it got really cold and you still had a big negative top of atmosphere radiative imbalance, which just made it colder and colder. And this is looking better, according to Zhang, for CSM3 development runs. I think it's kind of within the observational range for the last glacial maximum. So I'm going to show you some basic large-scale circulation metrics. So we'll start here with the upper tropospheric zonal wind. We've got DJF on the top and JJA on the bottom. This is for era 5. These are the biases that we had in CSM2. And then this is what we have now in CSM3. So there are definitely, I think, some similarities in the biases between these runs. A couple of things that kind of jump out to me initially is that maybe we have slightly worse biases in the summertime in the North Pacific. But in the Southern Hemisphere, I think there's an indication that we maybe have improvements in our representation of the jet stream. But to be a bit more quantitative about how the model is doing, what I'm showing here is the normalized mean squared error for the global map of 250 hectopascal zonal wind. So high numbers are bad and low numbers are good. These are all of the different CMIP6 models, so you can compare with them. This is in the pink range here is the minimum to maximum range across the members of the CSM2 large ensemble. And then here in green are these 3 chunks from the CSM3 pre-industrial control. And then in blue is the satellite era period for the historical simulation. So that's what it looks like for the global mean squared error. And I'd say it's somewhat similar to CSM2 overall in terms of the error. Here's the Northern Hemisphere. And so one thing to point out is that we do seem to have some degradations in our representation of the jet streams in the Northern Hemisphere summertime and autumn. And then here is the Southern Hemisphere, and we seem to have kind of pretty ubiquitous improvements in the representation of the Southern Hemisphere jet stream in the annual mean and in 3 out of the 4 seasons. Here now I'm looking at the lower tropospheric zonal wind, and so that is kind of picking out more the mid-latitude jet streams. These are the biases that we had in CSM2, and I want you to pay attention to the Southern Hemisphere because we've kind of had this persistent bias of having a jet stream that is too strong in the Southern Hemisphere. And that is what it looks like now in CSM3. And so something has changed. So CSM1 and CSM2 both had a Southern Hemisphere jet stream that was too strong. We still have biases, but they're different. So I feel like change is good. So because CSM1, this is like very persistent, but now it's too far equatorward in the Southern Hemisphere summertime and maybe even too weak in the winter. And so I think it'd be interesting to see whether the new gravity waves are playing any kind of role in that change. So here's the overall errors for a lower tropospheric zonal wind in the global view of it. And I'd say the errors are kind of similar between CSM3 and CSM2. Here's the Northern Hemisphere. Again, I'd say pretty similar. And then here is the Southern Hemisphere. And so even though our biases have changed, our overall errors, I think, are not reduced in the Southern Hemisphere, except for in the Southern Hemisphere fall there. And again, I think it would be interesting to see what role the new gravity waves that Julio is going to talk about are playing in that. Okay, here's upper tropospheric stationary waves in era 5. That's the biases we had in CSM2. And this is what we have now in CSM3. And so I don't really expect you to absorb everything here, but I think we have some similar biases to what we had before, but also some differences. For example, in the wintertime in East Asia, it looks like we have reduced biases in the stationary waves compared to CSM2. Here's the overall errors. Again, pretty similar errors in terms of magnitude to what we had in CSM2. That's in the northern hemisphere, also pretty similar. And then in the southern hemisphere, I think if anything, our southern hemisphere biases have reduced in the stationary waves, although that's not true in every season. Okay, the final large-scale circulation metric I'm going to show here is velocity potential in the upper troposphere. So this kind of tells you about the divergent flow. The divergent flow is coming out of the blue and into the red regions. So that's the climatology in ERA 5. Here's the biases we had in CSM2. And then here's the biases we have in CSM3. So definitely some similar biases to what we had before. I will just point out this particular region here where we have kind of too much divergent circulation over Africa and then convergent circulation over the Amazon. And this relates to precipitation biases that I think the development group are pretty well aware of, that we have is too dry over the Amazon and too wet over West Africa. And so these two things are probably connected and probably something we want to try and figure out how to reduce that. So here's the overall error in the velocity potential. And I will say that CSM2 was really an excellent model in this aspect. It was kind of, particularly in the summertime, is really the best. And I don't think things have changed too much in CSM3 in terms of the overall magnitude of the errors. So I'll just finish up with something about ENSO. Meg's going to talk more about ENSO in a few talks' time. But one thing we've been looking at is the autocorrelation timescale of Niño 3.4. So that's what you see here. This is showing all of the CMIP6 models and CSM2 and the observations. And so CSM2 did pretty well in this lagged autocorrelation. And these are also Hofmallers of ENSO event, El Nino events, so showing that CSM2 did pretty well in capturing this transition from El Nino into La Nina that you see in the observations. And so one thing we've been worried about is in the pre-industrial control, the autocorrelation timescale of the Niño 3.4 index is much too long. And when you compare with the other CMIP models, it's kind of worse than any of them. And that's reflected in not transitioning from El Nino into La Nina quickly enough in this model version. Just as an aside, the La Nina Hofmallers look pretty good. So I'm going to focus on this time at which the autocorrelation transitions from positive to negative and show you that as a function of time here. I'm using 70-year running means. And so here you see the CSM2 large ensemble and observations. And so they compared pretty well. And this is what our pre-industrial control looks like. And I'm capping the time at which I can calculate this at 24 months. But clearly it has much longer autocorrelation timescale than the observations. But interestingly, over the historical period, that kind of transitions to being better. And there's further indications that this is kind of dependent on the warming in the model, because you can also see it getting better in the abrupt 4x CO2 simulation. So it seems like if the model warmed up a bit, we might get more aligned with observations. And I don't think this is a signal forced by climate change. It's not there in the observations, but right now maybe the model is too cold. And that is kind of affecting ENSO somehow. And consistent with this, you see here in the Hofmaller on the right that at the end of the historical simulation, you start to get that transition into La Nina events. And so the model is currently a bit cold. And so maybe if we can warm it up a bit in the next round, these issues might go away. I just want to point out one other thing about ENSO, because I think it's been a concern that we've been lacking in ENSO teleconnections to the North Pacific. But Adam gave me these plots yesterday, and the one on the right is showing the ENSO teleconnection at the end of the historical simulation. And it looks very good compared to observations. So there's some indication that maybe if the model was warmer, El Nino would kind of fall into place. One more thing to mention, these are plots from Alice, is that the model also seems to have too extensive southern hemisphere sea ice. And so that maybe is consistent with it being a little cold. So that's another thing that people are keeping their eyes on. So to summarize, CSM3 has a lower ECS than CSM2. It has an improved representation of the historical temperature evolution. In general, I'd say the large-scale circulation errors are kind of comparable in their magnitude, but there are some changes. I think we have an improved southern hemisphere, but some degradations in the northern hemisphere. And we have an issue over Amazon and West Africa related to precipitation biases. There's currently some issues with the ENSO representation, but I think some of these maybe could be helped by the model warming up a bit. So see if they kind of fall into place. So that's all I have, and happy to take any questions if there's time.
You 700 diagnostics you did were from coupled simulations, right?
Yes.
How much do they change when you look at, prescribed SST? Does the relative goodness of CSM2 and CSM3 change when you look at F cases?
I don't know. I haven't looked at the F cases recently, but yeah, should do that. I was kind of, limited to what I could do. But you can
Okay.
I guess this machine just needs to run.
Yeah, and early on you showed the equilibrium climate response versus the transient climate response. What do you do for the transient climate response to actually improve that maybe a little bit? Move it to the right.
I guess we don't really know what the right answer is for either of those quantities. I think what we would want to compare with is the historical record, because the transient climate response is just the warming at the time of CO2 doubling in 1%. So we obviously don't have an observational comparison to that, but it's kind of a simpler metric of how the transient climate is evolving compared to historical runs where you've got aerosols and everything else happening. But what we can compare with is the historical record and the historical runs, and that looks good. It looks quite a bit better than it did in CSM2.
Thanks.
On the land temperature and time series, if you could go back to the slide. Not sure, but it looked a bit like wavy. So my question would be, is this like seasonal, sensitivity to something or is it long-term variability, or did I maybe just not look correctly? No, it wasn't this one. Was it? Yeah, it was this one, the blue line. The lower left.
The blue line is more wavy than the observations.
Well, I was thinking, yeah. Well, it kicks down and then it comes up. I was just puzzled by if this is due to a sensitivity to some forcing setting in, or if you know anything about.
Yeah, I don't know. It's a good point. I guess, the pink range would be the range of across the CSM2 members. So it doesn't look like it's more wavy. Like if the blue line was one member of the pink, I think the spread would be kind of similar in terms of the waviness, but it is a good point that it does look more variable than the observations. I haven't looked into it, but yeah, could do.
Right on time. Next, so we're continuing with our global evaluation with which we go.
So I too was waiting for run 121. So this truly is a working group meeting. So So we're going, everything Isla, I think, mostly talked about was kind of monthly and longer timescales. I'm going the other way. We don't look at these kind of aspects of the variability in the model that frequently, so I thought it was a good opportunity to see the state of the model in terms of variability. So does this actually work? No. So these are the simulations I'll be looking at in part or full, and so this is the key one, the 121. That's the most recent simulation, and caveat, as Isla said, this is not the final simulation. There's a pre-industrial and a end of 20th century, comparing to the large ensemble, also very quickly comparing to the CSM1 large ensemble. There will be a few CAM, so F cases later, and if I get to it, there's a sensitivity experiment that actually shows a very sensitive parameter that kind of covers a lot of the sensitivity we've seen and talked about so far with the QBO, for example. Has to be handled with care, let's say that. So with kind of daily and 3 hourly at 1 degree resolution, these are the things I think we can look at reasonably in the model, and I'll make it through nearly all of these, I think, maybe not the last one. If I don't, okay, so yeah, just to emphasize, everything is 1 degree, the observations, the daily and 3 hourly. And here's my thumbs of, you can agree or disagree. I'll show it again at the end and you can happily disagree, but I think this is, one thumbs up is, it's okay. It's not terrible. It's not fantastic. And so I would say in MGO, there are some concerns in the Darwin cycle predominantly. So the first thing I'll look at is blocking. And so this is somewhat of a simple metric that examines northern hemisphere blocking in the mid latitudes. So yeah, there's your ChatGPT atmospheric blocking. And essentially this is showing along a longitude in the mid latitudes, we're looking at the frequency of blocking there. So you have 2 characteristic peaks. This is in winter around the Western Europe, Northern Atlantic, and then over a lot of the Pacific. So, and these peaks are of order 20% in this particular metric. And so what is characteristic of all these simulations is that you have this northern hemisphere, northern Atlantic hole. And if we're looking at CSM3, which is the green, sorry, that is largely similar to the CSM2 large ensemble. So we're not doing particularly worse, we're not doing particularly better. So that's good news. Well, it's not the worst news it could be in terms of degradation. For northern hemisphere summer, this is less of a good metric for this particular characteristic. But again, we were kind of a little bit worse than the large ensemble, the first large ensemble, CSM1 and CSM2, but we're largely following those characteristics. Just thinking about why, we may have differences. In looking at all these, I saw that in March, April, May, we have CSM3 has a kind of peak that goes just about above all the spread of the other models, sets of simulations. And so I was thinking, well, what's different in mid latitudes and high latitudes that could kind of explain differences, and that's spectral element dynamical core. And I'd looked at this in old versions of the model, CAM5, just comparing the 2 spectral element finite volume. And if you look closely, it has very little influence on the large scale blocking in this particular model. So we'll see what this particular, it may be spurious, it's one simulation, but we'll see what we can understand about that. Second aspect, which is very gearish up here in the colors. We look at 2 aspects, 2 measures of the monsoon, the Indian monsoon, in this case, South Asian monsoon. The top one here is, I think it's useful metric to look at the phasing. So when is the month of maximum precip climatologically for these simulations and GPCPs, CSM2, CSM3. And, in observations, as you would expect, green is kind of June to the west. And then as it makes it further north, the kind of pale color here is like July into August for the most part. CSM2 kind of saw it a little bit late. Fewer greens out on the west coast of India and Vietnam here. And CSM3 is somewhat worse, I think, a little bit later in September in pieces. So that's, something we have to keep an eye on. Something more kind of stark is if you look at the actual, there's no measure of magnitude, amplitude here, but if you look at the evolution of the precip average between, you can barely see it, but between these two red dashed lines, and you can see the jump northward into the Indian subcontinent and then back down south. And CSM2, too strong, too far south, but then it was clearly affected by this very strong Himalayan maxima due to our perpetual problem of precip over orography being too excessive at 1 degree. We don't lose that in CSM3 here, but we can see that we have, it's arguable that we have a kind of more limited maximum precip, which is more consistent with observations here. Similarly, you can look at the little harder to categorize because there's a lot of interannual variability in North American monsoon. So this is the U.S., Mexico, and here the Gulf of something here, and so this again phasing. Monsoon, North American monsoon tends to be August in terms of its peak. Arizona, New Mexico here. And, it's definitely arguable that if you compare CSM2, CSM3 for that timing, it looks better. It looks quite a bit better. You're not kind of dominated by this excessive springtime bias that we've seen before in CSM2 along the Rockies here. So it's definitely arguable it's a little bit better. Marginal for the actual amplitudes and the northward propagation. You kind of get the secondary maxima here, but it does propagate further north. During this later period, July, August, September. Next thing, okay, moving towards the tropics. So, all right, so this is, shown these before, and hopefully I don't have to explain them too much, but basically these are 2D Fourier analysis in space and time of daily precipitation, at least 10 years in each case, two observed metrics on the top, and then CSM2 and CSM3 on the bottom. So it's essentially just showing you that the strength, the highest power of waves tends to be at long wavelengths and long time. So 30 days here. So we'll see again. So MJO is essentially down here. It's reflective of it. And we can see that we haven't made things worse, which is great between CSM2 and CSM3. You can argue, if you believe TRIM a little bit more for these high frequency and shorter wavelengths, which I think we do, that it looks better. And so we want to look at how do the decomposed waves look like. You can decompose waves by filtering from these sets of observations and simulations. So the guideline up here is basically observed. So key things we want to look at, there's kind of 3 key regions, which is Kelvin waves, which are this big, shooting off piece here. The MGO is this bright band here in terms of, it's the largest, most influential, if you like, consequential variability in the tropics on these time scales. And then there's these eastward propagating waves as well. So, overall going from CSM2 was not too bad. And I think I'll show for the MGO later that it is pretty good. It was an improvement from CSM1. But CSM3, I think, is looking pretty good in terms of Kelvin wave activity. The equivalent depth, so the actual speed of these is not quite right. There are smaller equivalent depths, so they're a little bit slower. But essentially, the picture looks good, even a little bit better. Now, these are for symmetric waves. So these types of waves here, Kelvin waves, they're symmetric about the equator. Another kind of set of modes to look at anti-symmetric about the equator. And this is, I've looked at these many times over the years, and actually, I've never really seen CSM capture this like this. This is a mixed Rossby gravity wave. So Rossby wave, depending on which way you're propagating, east or west, or gravity wave. We've never really captured this, so this is improvement. So my green thumbs up. They're just the one. It's not amazing. And there's a lot of pictures here, but basically, from the previous plot, you can take out the individual kind of regions of power maxima for those waves and say where geographically are these the most influential, the strongest. And so you can pull out these wave modes such that, we have trim on the left, CSM2, CSM3 on the right. So this is where we are right now. And so, yeah, there's these sets of modes, if you just take out the whole of that spectrum and call it the total of propagating waves, that's what you get. And, again, CSM2 for these metrics was a pretty good model. And I think CSM3 on the lot, for the most part, and I think it comes out is not a lot more, there's more variability. And I think some of that is projecting onto these wave nodes, such that the MJO in particular, for this annual particular picture, it's looking really good. It doesn't play out into the propagation, as you'll see next. But I think in terms of the regional and the amplitude, and the amplitude characteristics, it's pretty darn good. Kelvin waves, probably unsurprising, what I showed you before, a little bit too strong. And this is what I was saying, like now we say, okay, we have those, know something about the waves, but this is the MJO specifically, and it's a measure of how the winds and the precipitation are coupled on these intraseasonal timescales, and they basically you can see here, they propagate from the Indian Ocean, from that green dotted region into the Pacific. And so because it's going up, it's propagating obviously left to right with time. So trim and era is very coherent, as you would expect. And, CSM3, again, CSM2 was pretty good. CSM3 is equally good. It's arguable that it's a little bit too fast. It's definitely too fast to observations, but maybe a little bit too fast compared to CSM2. But CSM1, that's where we were incarnations ago. So it's the maintenance of that. And unfortunately, there's a thumbs down for this because if you look at AMWG simulations, you just don't get that relationship, which is really, I don't know what the word is, unfortunate. Which was common with Chem6 as well. So yeah, so this is a kind of thumbs up, thumbs down, which I've put. This is not subject to this was subject to modification. People look at it much more closely. So the next one was kind of question mark thumbs down, probably the worst thing, but I'm not totally sure I've got it right because there were some issues with the data. But this is diurnal cycle. I'll try and explain this a little slowly. So diurnal cycle here. So this is basically telling you, the color is telling you when is the maximum precipitation on average during the day. If I looked at several years of simulation, for trim it's 10 years. And so I've kind of marked it on here basically. So over land, greens, late evening into kind of late afternoon into kind of early evening observed. And then over ocean, in general, it is, during nighttime, during darkness, I guess, later in darkness. And the thinking is, and anyway, it's definitely the case that the greenness over most of these land regions is the fact that, convection has longevity. It's not immediately firing in response to surface forcing at midday. And CSM2 was actually pretty good. One thing, the amplitude, as you can see, was not as strong with the phase, the hue of everything. So the intensity of the colors is essentially the amplitude on the average. But for CSM2, it was pretty good. And again, this was an improvement similar to MJO from CSM1. But unfortunately, if I look at, this is where I'm a little unsure. This is actually CAM7 versus CSM2. But all things being equal, over land in particular, this should be fine. But as you can see, we've kind of retrograded, if I do that, but we've kind of retrograded back to CSM1, which is kind of unfortunate. So that's the final. Oh, okay, well, 34. Yeah, just to remind you that I think the blocking monsoons, the way that I've looked at them, tropical waves, coupled MJO look okay. I don't think there's a huge degradation, but there's not a huge improvement. But the CAM side, the prescribed SSC side of the MJO is pretty thumbs down, and then probably diurnal cycle is thumbs down because it's too early again, which is kind of a worsening from CSM2. Shall I show this? Yeah, I'll show. I'm gonna skip these. So one thing worth noting, I didn't annotate this, I didn't expect to show it, but essentially back to these two again. So the left-hand side here, now I'm showing top left of each one is observations, what it should look like. And then I'm showing CAM6, CAM7, and CAM7, where you back off a particular parameter that reduces the sensitivity to the increase in vertical resolution in the boundary layer. That's a lot, sorry. But essentially, this was required for a number of other reasons to moderate some of the spurious or overly sensitive behavior to the vertical resolution, particularly the surface thickness of the layer nearest the surface. And so when you add that in this bottom left here, then it looks kind of similar to CAM7. But if you take that back out, where it then has 58 levels, but without this kind of moderating influence, then you get this very intense increase in noise. Well, variability, but it tends not to be, if you jump to the next one there, to do with Kelvin waves anymore. So essentially, one of the problems is if you do not include this particular moderating factor, you destroy all the Kelvin waves in the presence of this high vertical resolution. So it's a bit of a mouthful, and I'm happy to talk about it. But this particular parameter is also the one that's responsible for some of the sensitivity with the QBO tuning. So we need to, it's a multi-dimensional problem, obviously. And that's it. I'll jump back to this. Thumbs up, thumbs down. Thanks.
Do you have any guesses as to why the diurnal cycle is degraded?
Always got to guess. I'm not too sure because I'm just wondering. I haven't even got a guess. I was thinking about it earlier and I was confused because I actually thought it would have gone the other way.
One more question. Do you think that the degraded diurnal cycle is related to the dry bias over the Amazon?
That was another thing. Yeah, good point. Thanks for reminding me. There is leeway into tuning based on this. I suspect we'll have some leverage on the dry biases. Yeah. As always, what else will it impact? Yeah. Good question.
Dave?
With all of these, you said keep an eye on a few times, or at least once. I mean, keeping an eye on that's great, but can we do anything about it? And which of these, like especially the ones that are degraded, do you feel like there's the CAM group would have any idea, or are we just sort of hoping that it gets better as we get closer to our final
I mean, the diurnal cycle, because it's a response to a forced problem rather than emergent phenomena like the MJ blocking is really hard to, that is what we would have most potential to make good progress with. But again, would that then affect all these emergent phenomena? I don't know.
Kind of related, if we had a warm enough to get the good INSO, is that everything gonna change here?
I mean, I didn't quite get it. I was looking like pre-industrial versus later, and I looked too, and like NGO, well, tropical wave variability increases in strength in the present day versus pre-industrial.
Did you want to answer Flavia's question, or should we pass it to Rich?
I have another question.
Go ahead.
Oh, yeah, my question was about the AMWG propagation. Is it of the MGO? Is it because coupled interactions are key, in which case it's not really a problem?
We looked at this a little bit in system 2, and it was, if you take the SSTs, this was in CSM2, if you take the SSTs from the couple model and treat them like they're an AMWG SST, it looks a lot better. So it's not necessarily a couple problem. It may be a piece of it, but you get a large part of it back if you just give it the couple SSTs.
So we have a right making a wrong, wrong making a right?
Yeah. It's weird. It's very weird.
What about Flavia's question over there?
See it? Sorry, I can't put my glasses on.
Read it.
So
With the MGO not propagating well in AMWG simulations, how much do you expect this affects performance of teleconnection to the North Pacific and North America?
This is, yeah, I mean, you're thinking about projecting short timescales onto something like monthly timescales. And That's, I mean, it goes back to someone asked the question for Adam's diagnostics, whether I looked at cases, yeah, just repeat. Yeah, that'd be a good test.
Adam has run.
No. No, haven't done it.
We're 1 minute late now. So, last but not least, the talk before the break.
Okay. So we've heard a lot about the development of CSM3, and I'm going to take kind of a retrospective approach, looking at how the El Nino Southern Oscillation has evolved. And I want to thank the co-authors listed here and a number of others. This work really wouldn't be possible without a big group effort. So really big picture, why do we care about ENSO? ENSO is the dominant source of annual variability in the climate system, and its warm and cool phases have important impacts on mid-latitude weather especially. So here in the figure on the right, we're looking at warm and cool anomalies and wet and dry anomalies associated with the warm and cool phases of ENSO. Importantly, though, the variability in ENSO might not actually be stationary in time. So that's something that I'm going to come back to a few times throughout the talk. And despite the importance of ENSO, Earth system models do continue to show some pretty persistent biases in how they represent the phenomenon. The ENSO amplitude continues to be either too strong or too weak in most models, so a bit of a Goldilocks situation where you just can't get it quite right. The ENSO diversity is limited, and in particular, SST anomalies tend to extend too far into the West Pacific. And all of this is complicated by a relatively short observational record. So again, variability might not be stationary in time. And to illustrate this a bit is a figure from Wittenberg in 2009 looking at the Nino 3 power spectra over a really long-running simulation of a different model, CM2.1. What I want to highlight here is just the spread across each of these different colored lines. So if we take 20-year slices of a long-running simulation, we have a lot of internal variability, and it's difficult to say exactly what the right answer is. If we take even 100-year slices of a long-running simulation, there's still a fair amount of variability happening. And it's really not until you have 500 years of a simulation that you can kind of start to narrow this down. And so, especially as we go through model development, 500 years of a single simulation is asking quite a bit of our computational resources. And I do want to highlight that CSM2 also had a number of ENSO biases. And one of the things we did during development was implement a new parameterization that Peter mentioned earlier to try and mitigate some of this. And this is the convective gustiness parameterization. So the idea behind this is that when you have deep convective precipitation, what happens is that you get these outflows near the surface that result in gust fronts driving enhanced surface fluxes and enhanced near surface turbulence. In the late 90s by Jabuli et al. And in the early 2000s from Redelsberger et al., they noted this nice relationship here in a black curve that relates rainfall in centimeters per day on the x-axis to a gustiness wind speed on the y-axis. So what we did in CSM3 is basically implement this curve to increase near surface wind speeds as a result of convective rain rate. So to give you an idea of what this looks like, this is a roughly 20-year AMIP simulation, so active atmosphere and land. Here on the left-hand side, you're looking at 10-meter wind speeds in a control case without this gustiness parameterization active. And I've highlighted in black contours where we would consider relatively weak mean surface wind speeds. And these regions overlap nicely in the middle panel with regions where we have pretty high convective rain rates. So really we're targeting the tropics with this. And on the right-hand side is the gustiness speed that we're adding on top of our mean wind speeds. And again, really focusing in here on the tropics. So this is something that we would expect to have an impact on ENSO. And I'll show you in a minute that it does, which is good news for me. But more broadly, how has the representation of ENSO actually evolved throughout the development of CSM3? And one thing to note is that we're leveraging a variety of development simulations. So this is a little bit different than kind of a classic scientific talk where you make one little change, run it for a long time, and look at that difference and how it impacts ENSO. These are all fully coupled model simulations. Atmosphere, land, and ocean are active, and they're all run with a pre-industrial climate. So I won't be showing you any of the historical simulation that Rich talked about. As possible, we validate these against observations and reanalysis. But one thing that I think is really fun to look at is adding context from previous versions of the model. So I've taken long-running pre-industrial simulations of CSM1 and CSM2 that were submitted to the CMIP archive, and basically just chop those into 40-year pieces to get a sense of internal variability within the system. We'll also note that there's a bunch of other new developments that have gone into CSM3, as you've already heard earlier. It's not just convective gustiness, there's changes in the ocean, there's new radiation schemes, so just keep in mind that this is a lot of things going on. I thought I'd start with some positive news. So are there characteristics of ENSO that have improved throughout the course of development? One thing to highlight is the strength of ENSO events. And so here we're looking at the annual cycle of SST anomaly variances in the Nino 3.4 region. And you can kind of get a sense of that annual cycle nicely. So in observations, we have a peak around 1.5 Kelvin squared in the Nino 3.4 region, occurs in boreal winter, and then the minimum occurs closer to spring, a little under 0.5. And as you're going through model development processes, looking at hundreds of these panels next to each other, it becomes really difficult to tell what the difference is. You'll go blind way too fast. So I'm going to narrow this down into a single line. So here again, we have our maximum monthly variance, our minimum monthly variance, and then the mean is marked here with the dot. So how did this look in previous versions of the model? So here are the pre-industrial ensembles of CSM1 and CSM2. You can kind of get a sense that CSM2 amplitudes were maybe a little bit stronger than CSM1. But if I pick out 2 simulations from each of those kind of ensembles, it becomes more difficult to say that they're dramatically different from one another. So there's a lot of internal variability within this metric that's important to note. And if we look across model development versions more recently, here on the left-hand side is simulation 38. To give you context, here the most recent, we're at 121, so some things have happened. Starting early on in the development cycle, we see a behavior that's more similar to CSM2, right? Our amplitudes are pretty strong, and then they start to come down. Maybe we overshot a little bit recently and our amplitudes are really weak, but 121 doesn't look too bad. In terms of what's driving these, it's kind of fun to walk through each of the model development versions and figure out what changed. When we added the convective gustiness parameterization here in run 61 to 64, we decreased our amplitude in a positive way. When we turned it back off as a sanity check, the amplitude of ENSO went back up. So that was a good sign that this is having an impact on ENSO amplitude. More recently, in run 104, so we've been running with this convective gustiness parameterization active, we turned it off in run 109, and we see a shift in ENSO amplitude that is in the same direction as before, but it's much weaker. And that's because we have all of these background changes happening as we're developing CSM3. And so it's kind of muted the impact of the convective gustiness, although it is still present. What I also want to highlight again is this issue of internal variability. So we have run 21 is 200 years, but we also have run 98 was over 200 years. So what I've done here is split run 98 into 2 halves. So the first 100 years versus the second 100 years. And even though everything within the simulation is exactly the same, we're just cutting it in half, you can get a different answer in terms of how ENSO amplitude is behaving over that 100-year segment. So even with 100 years, it's hard to say exactly what's happening. But overall, SST anomaly variances have improved in the Nino 3.4 region, but it's complicated when you have so much internal variability, even within the CSM1 and 2 pre-industrial ensembles. Now, a bit of bad news, there are characteristics that haven't necessarily improved. And in particular, I want to talk about the spatial extent of ENSO events. So as I mentioned, the SST anomalies typically tend to extend too far to the west in most models. This was true in our model as well. So here we're looking at observations, and we're looking at the lag zero correlation between SST anomalies and the Nino 3.4 index. So here in the Nino 3.4 region, which is boxed, that correlation should be really strong, and it is. So that's a good sign. The math is working. If we look at the 0.5 contour line, so this is kind of where I'll mark a strong correlation. It extends a bit into the West Pacific, and then we get a switch in sign of correlation a little bit further out, which is marked by a circle. So again, to kind of condense this down into a single plot, here we have observations. In the middle panel, we're looking at the westernmost extent of the 0 contour line, so how far between we get a flip in sign. And then in the right-hand panel is that 0.5 contour line. So how far do the strong correlations extend into the West Pacific? And if you're like me and you don't normally think about a map with longitudes on it, here's something useful for reference. So CSM1 and CSM2, again, we see a lot of spread across each of these models, but none of them really do a fantastic job at this metric, right? So we've been looking at this bias for a pretty long time in terms of CSM history, where the ENSO anomalies in SSTs extend too far into the West Pacific. And this is not something that we've necessarily solved throughout the course of CSM3 development. So again, at the top, we're looking at the furthest from now simulation, so run 38 down to 121. The 0 contour line is actually pretty insensitive to model changes. So even though we're making really big changes, this metric is hard to move. Now on the flip side, the 0.5 contour line is a little bit more sensitive. And so this might be a region we can target for model development moving forward. But again, I want to highlight these 200-year simulation parts from 198, you get fairly different answers. And that's with 100 years of simulation. So again, the internal variability here is going to make it hard to say that exactly we are improving or degrading the performance of ENSO. So the spatial extent is a consistent problem across every version of CSM, including CSM3 as we're developing it. The core area of strong correlations is more sensitive to model changes relative to the, compared to the full extent of the SST anomaly correlations. And one of the challenges here is really attributing what's driving these changes. So because we're doing this throughout model development, we have a lot of different moving parts. It's not often that we change one thing and look at the impact. But one of the exciting things that's come through is that there are these possible connections between SST, raw, whether it's too cold or too warm, and what's happening in ENSO characteristics. And so Isla mentioned earlier, this might play a role in the autocorrelation time of ENSO, but it also plays a role in how far into the Western Pacific we have these anomaly correlations extending. So here on the top, we're looking at our observations for lag 0 SST and Nino 3.4 again. And on the bottom is the annual mean SST itself. And I've highlighted as a contour of the specific cold tongue, the 299 Kelvin. And again, just marking that westernmost point here with a circle. There's a pretty strong relationship between those two characteristics. So here on the y-axis, we're looking at the westernmost point of the 0.5 correlation for SST anomalies. And on the x-axis, we're looking at the westernmost point of the cold tongue. And there's this nice linear relationship that in particular scales with the mean SST within the 3.4 index as well. So each of these really cold simulations are dark blue, and they tend to have a really strong bias in the western extent of ENSO anomalies and a really strong bias in the cold tongue. If we move forward in time when we have these warmer simulations, things look a little bit closer to observations, but even for observations, it's kind of way far up in the upper right-hand corner compared to these model runs. So it's been difficult to get this right. And again, to add a little bit of context here, what I've done is add those 40-year segments of CSM1 in triangles and CSM2 in squares shaded by their mean SSTs. We see a similar relationship across CSM1 and CSM2 as we do in CSM3, but it's a little bit more concentrated, right? And so if we look at the CSM2 Korean Industrial Ensemble, we are getting these yellow squares, which means our SST is doing a lot better in CSM2 than we did here in CSM3, but we do still kind of see this scaling of, as you have a more Western cold tongue, you have a worse extent in your Western ENSO bias. So just to summarize a bit, there are things that have improved throughout the course of development in terms of ENSO characteristics, but there are also some that have not improved. And one of the important things to note is that when we say we want to improve ENSO, it's important to note which part of ENSO you actually want to improve. So improving one characteristic does not guarantee that all characteristics improve. Even for something that does show general improvement, like we saw with the amplitude of ENSO, we are struggling with really high internal variability, where even 100 years might not be enough to understand fully what is happening with ENSO. We have seen at least that the mean SSTs seem to play a role in this. So when you have your SSTs that are too cold, it does look like that extends the Western extent of the ENSO anomalies and may play a role in the amplitude and the autocorrelation time as well. So with that, I will stop and I'm happy to take questions. Thanks.
Thank you so much.
Hi, nice talk. I'm curious about the asymmetry and the magnitude of La Nina and El Nino in these simulations, or if you know if they have different maximum amplitudes.
That is an excellent question. I haven't looked at that, but that would be really good to start looking at. Yeah.
Because the correlation, the zero line might show that you have a lot stronger La Ninas, which is something that I think was kind of present in CSM2.
Yeah.
So that could be, yeah, in a sense, highlighting that what you need to boost is your convective wind response to SST anomalies.
Yeah, no, that's a great point. I've been super biased on El Nino in particular versus La Nina, but that's another metric we should look at. Yeah, excellent point.
Did you look at all, because it seems all your simulation are 1850 PI control,
Yeah.
but now the 121 is completed, it just completed recently, but
Yeah,
do you think it can make a difference in your dot?
I haven't fully looked at it. I started running the analysis this morning. My guess is yes. I think especially with the results that Isla
Yeah,
showed.
that's what
in
I'm thinking,
particular. Yeah, it's warming up, so it should be doing a better job at Western extent, at autocorrelation. I'm not sure on amplitude, but we're in an okay place on amplitude right now, and so I would hope that it wouldn't change dramatically. But yeah, I think that's worth looking at.
I mean, it's not a question as much, just reminding all ourselves, you said the vertical coordinates of some of the ocean has changed, but to be fair, the whole ocean has changed.
There's that. Yeah.
So what's just interesting is that some of these biases are persisting with a brand new, completely new ocean.
Yeah, especially that like western extent of the zero contour line. I would expect it to have been more sensitive to changing the ocean model entirely. But-
The ocean doesn't matter.
Mhm.
And Rich just showed the dicot doesn't matter.
Yeah,
either.
sorry. So I was saying that, I was.
All righty, so we have a break for half an hour now. We have light refreshments out here. Thanks. Eagle. Going, the last session of the day, so give the mic to Natalie. Natalie has to run to a meeting at CSU right after your talk or after, yeah. So, yeah.
Thank you so much for jamming me in here, kind of inappropriately. Going to make you all think about aerosols for a little while, and I'm sorry about that. It was very nice of the organizers to sneak me in. I could only be around for this afternoon. I'm just going to talk about the AeroMap, a new data compilation of in situ observations for PM 2.5 and PM 10 aerosols. You can see the billion co-authors as we try to gather all the data and include the co-authors that took all this very difficult data and make sure they get credit for it. It's a paper under review and the data set is available on Zero. So what we put together here is about 15,000 station data sets, over 20 million observations, individual observations. And, you know, most importantly, it includes data outside of the US and Europe, where most of the previous compilations only included that data. Our goals in the study were really to identify and compile aerosol data sets so that other people could use them, understand the spatial distribution primarily. It's the largest source of variability for aerosols, but also look at some temporal trends as well, and try to put together an easy to use data set. Most people just use the satellite remote sensing data sets just because they're available globally, but they actually have a lot of uncertainties. They're not perfect data sets at all. So the surface concentration measurements are ground truth measurements. They're available during cloudy time periods. Of course, satellites aren't available during those time periods, or surface-based remote sensing. The surface concentrations provide you with composition, and that's super important to know the radiative forcing. The aerosol optical depth doesn't give you anything about composition. It's almost unavailable from the remotely sensed data. It's only available when your AOD is over 0.4, which is huge. We need to know also the composition to know what the trends are going to be. I mean, if the sulfate goes down, if we actually get off fossil fuels, that would have a completely different trend than if it's a land use source like something like ammonia or something like that. Those have very different trends in the future. And of course, we need the surface observations for air quality studies. Surface concentrations can also detect very low versus low concentrations. The remotely sensed AOD really, it only varies over one order of magnitude, just because the AODs have a lower limit of about 0.03 or 0.04, depending on if you're over land or oceans. Mostly we try to present a climatology of basically all the data, just so you can see where the data is. And the reviewers thought that this could create a huge bias, but the truth is, we really, really care about small trends in aerosols. It's really, really important, but not when you're doing a spatial comparison. That's not very important. You can see here the climatological concentration over 1986 to 2023, and the decadal concentration, just an average over 2010 to 2019 in the data set for PM 2.5 and PM 10. And you can see it follows pretty much for almost all the data, the one-to-one line. Remember, there's 15,000, there's 7,500 data points on each of those. So you can see that there's a few that are outside that range, but pretty much it's a one-to-one. So very important for temporal. The temporal trends are very important for climate questions, but when you're trying to compare to the model, it's not that important. They're just a few percent, 20% difference doesn't really matter in terms of your surface concentration. Just because you have the surface concentrations vary over 2 to 3, 4 orders of magnitude, of course. So factor 2, you can't even see on this plot really. There's several sources of uncertainty in this kind of in situ data sets. If you take a look at either in a model or the observations for aerosols, they have very, very short pollution events. That's where almost all the mass is during very short time periods. So the temporal variability over, less than a month time period tends to be really large. But the interannual variability, for example, tends to be smaller. So we use a normalized standard deviation to try to take a look at how you should compare the model to the observations here. And the measurement errors are, the reported measurement errors for each of the data sets. Interannual variability here, I've already mentioned, it's rather small. It's about 0.15, I think. The measurement method matters more because some methods use dry aerosols versus wet aerosols. That matters more. Then within grid variability, because so we just kind of average what all the aerosols were within a 2x2 grid just to get a sense of, or within 1 degree to get a sense of what the errors are from that. And you can see that's quite large, but the within year variability is the largest variability for each individual spot. We tend to plot it using a 2x2 grid, but all the original data is also there. It's just you can't see the data if you don't grid it up a little bit. So overall, we get a normalized standard deviation if we assume these errors are independent and we square and square root them, then we get a total of 0.6 is the normalized standard deviation. So we're just going to use a factor of 3 as the uncertainty here across 4 orders of magnitude observation. So showing you again in the PM 2.5. So the background is the model output from the CAM 6. Okay, it's slightly modified. We modified the dust a little bit, but otherwise it's the CAM 6.1, I think. Here, and then the dots show where the observations are. And you can see, we have the US data. We also got the Canadian data, which is surprisingly is not included in a lot of data sets. The European data that a lot of people have is there. We also have data from Turkey and Israel, just because we happen to have people from those countries in our group that could translate into English. Same thing with China. India was in English, but extremely painful to download. Chile, here's downloadable, and South Africa, and then Australia and New Zealand aren't always included in this. So it generally has about 8 times as much data as the other data sets that have been available there. You can see here we're plotting the scatter plot, and we use a 3-fold uncertainty there for the different regions. And then for each of the regions, we average it just so you can get a sense, because once again, there's just too much data plotted up there. So we average over the regions, the model, and the obs, and that's what the bold black things are there. This is when you grid it, you get about 0.6 R, and then a higher correlation coefficient if you have it ungridded. So the model, one interpretation might be in the places where you have a lot of data, industrialized regions, you actually know the aerosols better than in other places. And so when you average over though, you lose a little bit of your correlation coefficient. We also have then constituents as well. So we have the sulfate, black carbon, for example. And you can see, for example, that the model is a little bit on the high side for the sulfate, which is consistent with previous studies. And black carbon, the Europe is a little bit low in the model. We have organic matter here as well. The model's doing okay there. Sodium, maybe there's evidence that there's actually sodium emissions over land regions. We don't have it in the model. For dust, which of course I obsess about a lot, we're on the high side, which is consistent with our other studies. Like CESM, many dust models can't match the surface observations, the AOD and the deposition at the same time. There's just a disconnect there. So you kind of have to decide what you're trying to match. And for these runs, we were trying to match the AOD. And of course, we don't do as well then for the surface concentrations. There's also the nitrogenous aerosols, the nitrate and the ammonia here, and we don't have it in the CAM 6. So we're actually using a run with the CAM, and we're just adding those on to that. Wouldn't say we do great in the model. The particular CAM that we're using here does not have a thermodynamic version, so we would do much better if we had that in there. So we also have the same kind of data for the PM10 as well, so two different sizes. There tends to be less constituent data for the PM10 size, but everything that's available then we put into this data set. It's all available in that CDF format. We also added temporal variability as well. So annual averages for each of these at each of the stations is available in the database in the NetCDF file. And you can just see some of the trends, for example, in the PM 2.5 across different regions. We're seeing some decrease. You actually get larger decreases, say in Asia in PM10 than in PM 2.5. We also put out the climatological monthly mean, so you can take a look at the seasonal cycle and the quality of the seasonal cycle. And it doesn't show up very well here, but in a lot of places we're getting the red colors, which means we're getting the correlation coefficient, right? So here we're taking, we have 12 months from the model, the monthly average, 12 months in the observations, take the correlation coefficient, see if you get the seasonal cycle, right? You can see in a lot of places it's red. That's good. We get the seasonal cycle right. But there are places here in India, some parts of the US, Turkey, where we're actually getting the seasonality wrong in the model. I'm not sure anyone's taken a look at that before because we didn't have easy to access data sets. So this would be interesting to use to help out, but this is all included in this data set. Just want to point out that most of the areas of the globe, even of land, we don't have data, right? There's very little in situ data. And if you want to know what the chemical constituent is in the real world, then you would actually need observations in those regions. So we need more surface observations. The model does not include the nitrate aerosols, this version of the model, and right, it won't be in the CMIP7 simulations either, right? You'd have to run the CAM-CHEM to get that. So that's about 10% of the global amount of the aerosols, but in some regions, it can be 50% of the mass we're missing. So if you're trying to look for regional trends, then yeah, you have to have the nitrogen species. This has already been pointed out in other papers, but we're still running without the nitrogen aerosols for the climate model simulation. So you just have to recognize that in those regions you have pretty strong biases locally anyway. So summary conclusions, right? We have this new compilation. We tried to make it as easy to use as possible in that CDF format, and everything tries to link it back to the original data source so you can check in, if you want more information. We include much more data in the non-US and non-European areas than most data sets do. We include composition as well whenever that data is available. We need more in situ data to try to constrain what the actual aerosol distribution is in the current climate. And the models like the CESM, we really need to be including unfortunately, the full chemistry, which is very painful for the time trends in order to get the local trends in different places. I will also say what I talked about last year. I think it was last year, just the other paper that we had just pointed out that we know, even less what was happening under historical or paleoclimate time periods, and in particular, the biomass burning in the CMIP6 data sets does not match available observations and actually has the exact opposite trend as the available observations. We don't know for sure what it is, but it has the wrong trend. And so, especially if you're looking at anything before 1980, just remember your aerosol uncertainty is probably 1 or 2 watts per meter squared, just from the emissions, just because biomass burning is so important for radiative forcings, and it is so uncertain, and it could just fluctuate up and down. So just keep in mind the aerosol uncertainties. Thank you.
Question from Emily. Was the temporal resolution good enough to do event-based analysis? Yeah.
So here we just like monthly mean climatological, but we have all the data. Okay, we can't repost it. Super happy. So if you want to get it, super happy to give it to you. But some people won't let us repost it. So, right. So that's what we basically say. I mean, it's a ton of work to put together this data set. We're so happy to have people use it. Okay, so just let us know. And we're trying to get everybody to post all their data and then they wouldn't care if we reposted it in one format.
The biomass burning trend, you said it's the opposite side. Can you just, what's the correct sign and the wrong sign?
Okay, the CMIP6 has an increase between pre-industrial and present day in biomass burning, and the very limited ad observations suggest actually a decrease in biomass burning.
I think is that just in the recent, like since the 40s or 50s, or is it go
I'm
further back?
talking ice core to pre-industrial, to 1850 to present day.
Okay.
And I'm using the paleo data. This is all very uncertain, but there's a group called Environment trying to put together a different trajectory of the biomass burning so that we can try to do some runs with it, and hopefully before CMIP7 is put out. The dust is also very wrong as well, which of course I need to care about. And Danny Leong is writing a paper on that. It doesn't matter as much. It's the biomass
Yeah,
burning.
no, we know, I know about his paper.
Yeah, but it's 1 to 2 watts per meter squared. We're talking about uncertainty in biomass burning if you don't know the emissions. So it's pretty big.
I mean, we're in the process of trying to figure out if we went with interactive fires. But that would probably just be even more wrong. I mean, I don't know, it's different. We're internally consistently wrong.
Yeah, I mean, okay, take the case of the dust, right? And we put everything in there and we try to make it as right as possible. And Danny's new algorithm is better, but we still can't get all the processes right. And so we'll probably have to force the models to get the right trajectory. Okay.
Yes, yeah.
So if we've evaluated the couple biomass burning code, but I'm not sure that it's up to this particular task. So we have to watch it.
So we're having a conversation here about that, but the CSM does, or CLM does get the sort of decreasing trend from at least the middle of the 20th century to present day due to human, basically, it's driven by fire suppression.
Yeah, well, that's awesome to hear. That's a really big improvement. The one thing when you go from 1850 to present day that you want to make sure you get right is the agricultural fires. And I don't know if that's in the model.
It is, whether it's right.
But hey, might as well look at it then, because maybe it would work better. That'd be super cool. That's fine.
Okay. Still in time. So now to the much anticipated moving up this talk. It's all biases in the model. No pressure. Okay. You want to wear them?
Okay, so your name is on this talk.
Yeah.
The blame is spread. Okay, yeah, I'm gonna talk about, the moving mountain source and also a little other, some stuff on other gravity wave sources. And I'll really be focusing exclusively on the southern polar vortex. The quick outline. I'm going to give some background first and show some results from high resolution runs. Then I'll talk about the sources in CAM7 and just some brief summary and plans. Okay, so the problem is basically this. Like in many models, the southern winter polar vortex in CAM is too strong, and that is, related by thermal wind balance with it being too cold. So that's the problem, and it's a problem that exists in climate resolution models. It's existed for a long time. People have tried to explain it by having, invoking missing drag from islands, etc. But anyway, it's been in models for a long time. It was in CAM6. It's not as bad as it seems to be in CAM7. Unfortunately, in CAM7, it doesn't, the bias that we see doesn't seem particularly amenable to the sources of gravity waves that were present in the model in CAM6, and that's essentially just fronts, convection, and mountains. I'm not sure why that is. It could be there are a couple of differences between CAM7 and CAM6. It's got higher vertical resolution. It has a new dicore, which is a cubed sphere, and that's I think quite different from what was there before. It was a Latlon FV, so there were things in the gravity wave code like tapers that made things graceful as you went to these tightly spaced longitude line or tightly spaced longitude lines as you got to high latitudes. Okay, so then for the rest of this talk, I'm going to discuss some possible solutions to this problem. The first is resolution, and then I'll just reintroduce some new sources for a new source for the gravity waves. So here we are. This is a plot of zonal winds and zonally average zonal winds and temperatures in CAM7 here. This is a very recent version of the model, except I've turned off any new gravity wave sources. So this has only the sources that were there, have been in CAM since a long time ago. Fronts, mountains, stationary mountains, and convection. So here's the problem. The polar vortex is very strong. It's in excess of 120 meters per second, much stronger than you see in ERA. Oh, there we go again. I think if you tremble a little bit, this thing just zips. Okay. So clearly not. Okay. So, and really probably more important for other parts of the model is this, that is that the stratospheric vortex in winter is really way, way too cold. And, God damn it. Sorry. And that problem, I'm going to stop pointing, and this is the last time I'm going to try to point with this damn thing. I'm just going to walk up to the screen and point. This problem, this problem extends into spring. So here we have the springtime polar vortex is too cold compared to observations. That's a problem for chemistry because, the sun comes up and things happen. Okay, so increased resolution. We've been interested in increasing the model resolution for a while, so we have started to do things at higher resolution. I'm going to talk a little bit about this in a second. The runs I'll talk about are prescribed SST runs. They all use the 93 level. I should have mentioned that before. I'm showing results here only from the 93 level mid-top model, which has a top round at around 85 kilometers. And so we tried 27 kilometers and 14 kilometers, NE240. And in anticipation of the fact that, we'd be resolving, frontal circulations just great, we decided to disable initially the frontal scheme in these high resolution runs. And that turns out, I'm not going to dwell on it here, but just FYI, don't do it in a quarter-degree model. Okay, so these are the results from our high resolution runs. And I have to, when I was looking at this talk 5 minutes ago, deciding whether I should make more edits, I realized that I believe these quarter-degree runs actually include the moving mountains. So ignore the quarter-degree runs here. But what you do see is going from the 100 kilometer 1 degree run to 8th degree, you do see that the polar vortex does get quite a bit better. In particular, look at the temperatures. Oh, I touched it. Look at the temperatures. They've actually gotten pretty close to observations in the 8th degree. So what's going on? Resolution clearly helps. Obviously, it's extremely expensive. The one simulated year of 8th degree costs about 5 million core hours. So we can't realistically, propose this as a solution for our polar night problems. But we can learn from it. So this is a movie, which I hope will work, of the the 8th degree simulation. The gray shading is vorticity in the boundary layer. It's absolute value of vorticity. It's relative vorticity. So, you see lots of nice swirly things. You'll see a hurricane occasionally in the North Pacific. I should mention this is for July. So it's southern winter, northern summer. Oh, it was supposed to loop. So what you see, and the red blue shading is vertical motion at 44 kilometers. So vorticity at 1 kilometer, or no, actually, sorry, 5 kilometers, so near the surface, and omega at 44 kilometers. And what you see is that there is actually some correspondence between the stuff in gray and the vertical motion in the mid stratosphere. So, it looks to me like the things are moving at about the same speed, and where you see gray, you often see, blue and red. So this is suggesting there's some connection between whatever's producing vorticity in the boundary layer and vertical motion in the 8th degree run at 44 kilometers. So this is an analysis of resolved momentum flux in the model. So not parameterized, resolved momentum flux at 1 degree, quarter degree, and this is actually, you can look at this, and 8th degree. So what you see is that as you go to higher resolution, you get more resolved momentum flux all the way up to about, up into the upper stratosphere, even lower mesosphere. So this is, this is a way to, the positive momentum flux here, it's sort of opposite to the usual convention when you use vertical velocity in geometric coordinates. Positive here means drag. So where you see lots of orange up there, it means waves are dragging the zonal wind from excessive westerly state to something closer to reality. Okay, so the fact that even at an 8th degree we get some improvement, there's clearly something we might be able to parameterize in the model. So as I mentioned before, the pre-CAM 7 sources are convection, deep convection that is, orography, and fronts. And as I mentioned before, none of these current or former sources really gave us the leverage we needed. So we proposed, Martina, Joan, and several others, adding a new source last year at AMWG. We called it the moving mountain. A lot of people get irritated by that, but it's basically just, it's just a low phase speed gravity wave source that's forced by a relatively steady circulation that moves somewhere in the atmosphere. It could be anywhere, but I'm thinking it's somewhere in the lower troposphere, and it's launching gravity waves with low phase speeds, which are what you need to drag the polar vortex, sort of get it into shape. So our first attempt, which we proposed last year, was keying off of PBL momentum fluxes. That was before we did these high resolution runs. So now we wanted, we're proposing a second potential source for these waves, vorticity. You could see in the plot that in the movie, you could see a real connection between lower tropospheric vorticity and stuff happening at 44 kilometers. So we are, you know, our current proposal to people is that we should parameterize a source of waves with low phase speed launched by vorticity in the lower atmosphere. So the PBL source that we proposed last year, they give comparable results, and I'll show you that in a second. You know, the advantage of the vorticity source is that it is actually, you know, referenced in the literature. There are studies that propose a vorticity source for gravity waves. And the PBL source it's been difficult to validate. I think we have some ideas about how we might go about this in the future, but it's proven difficult to validate. And the vorticity source, furthermore, as the movie implied, the vorticity source is supported by our NE240 results. And what you see here are Hofmullers of vorticity, in this case at 1 kilometer, momentum flux. So this is actually what's dragging the atmosphere at 20 kilometers really. And then there's an overlay of this and that. And all you really take away from here is the notion that, you know, some of these streaks in vorticity align pretty well with the momentum flux at 20 kilometers. And, you know, just FYI, these are the Andes. I think this is New Zealand and maybe Tasmania. So, you know, you see the steady actual mountains there too. So this is then where we are now. On the very far left is kind of the pre-CAM7 sources. This is the L93 mid-top model. And, you know, I've already shown this field before. And right next to it is a current attempt with the vorticity source for the moving mountains. And you see it has captured, it's improved the simulation quite dramatically, both in wind and temperature. So the temperature now in the southern hemisphere winter polar vortex, the temperature is now pretty good. Just for reference, you know, the momentum, the PBL momentum flux source gives similar results. And over there is ERA climatology. Okay, so I want to just kind of end by showing what tendencies or what forcing some of these different sources produce in the model. So this is a 1 season mean of tendencies on zonal wind induced by the three sources you might expect to have an impact in the southern hemisphere polar vortex. Mountains, fronts, and what I mean by is the current frontal scheme. And then on the far right there, or whatever that is for you guys, the moving mountain scheme. You know, so, you know, just FYI, this is a feature that people in southern, you know, in gravity waves like to point out a lot. The gap at 60 south in the southern hemisphere, sort of the Drake Passage gap, where, you know, you can go all the way around the world on a latitude circle and not run into any topography. See, I think it's the only place on, not 60 exactly, but that part is where it happens. So here's the frontal scheme, and over there is the moving mountain scheme. Oh. So one thing that really surprised me, and I think it's part of the reason we're having trouble tuning the model without an additional source, is the fact that the current frontal scheme
actually produces a really substantial acceleration of the flow. So instead of dragging the winds back, the frontal scheme is actually trying to accelerate winds right in the lower stratosphere in the southern hemisphere. And yeah, that's what the orange color means, positive. In this case, it means acceleration. And the moving mountain scheme, it's dragging the lower stratosphere. Yeah, I'm going to ignore everything that's happening north of zero for now. You know, one other thing that we're interested in kind of chasing down a little bit more is, you know, there you can see that the pattern of tendencies once you go above about 50 looks fairly similar between the moving mountains and the frontal scheme. It's not surprising, maybe. I don't think it's necessarily bad, but it's definitely something we need to look into. All right, so that's it. The summary is basically that moving mountains improve the southern polar vortex. And I didn't show it here. I have some pocket slides that I can show you that back me up here. The moving mountain doesn't degrade the northern hemisphere significantly, or at all, actually. We're still tuning. I know there's a time limit to that, but I think until the ocean gets itself straightened out, we've got some time. We're exploring, some of us are exploring a potential collaboration with Will Chapman here in CGD and Hamid Pahlavan at NWRA to do some automated tuning of the various knobs we've got now. Well, that's it. You know, we're going to do some nudging runs to ERA 5, probably also some, you know, nudging to fine to the NE 240 results. That might give us some insight. And finally, we're hoping that the Loon Balloon momentum flux data, which is a product that's become available recently, might give us another way of validating these schemes. So that's it.
I'm wondering if you've noticed any relationship or correlation between the temperature over the South Pole and the surface stress in the Southern Hemisphere storm track?
I haven't. I've been looking for, you know, some impact of these gravity wave schemes on the, on our, you know, well-known stress bias in the Southern Ocean, but I can't say anything about that right now.
Okay, so you've looked for it, but you haven't seen it.
I haven't looked for it very much.
Okay. Okay, but by thermal wind, there should be some
Yeah.
relation.
Yeah. Yep. But I don't have much. Yeah, I'll.
In your high resolution runs, did we switch off gravity wave parameterization?
We switched up a frontal scheme, not the other
Only
ones.
frontal
Yeah.
scheme. And how much you think that effect of a high resolution and lateral propagation of gravity waves important in the free atmosphere versus the sources, what you would like to parameterize?
I mean, I think lateral propagation, I mean, even at 1 degree, I think lateral propagation is an issue. I don't know if it has an impact, you know, a large impact on zonal mean climate, but it definitely has an impact on where waves break, because as they laterally disperse, their amplitudes go down and they break. They can propagate higher before they break. So I think lateral propagation is something we have to parameterize, but I don't know if it's going to make an order 1 difference.
This is actually what you discussed when you got gap of South Georgia Mountain. This is basically lateral propagation.
Yeah. Yeah. No, I won't deny that it's an issue.
Yeah. And this is probably most important. And also, you did not mention about the simplification of this gravity wave breaking criteria, which is, well, might be also impact somehow.
You mean the Linsen?
Yes,
assumption?
yes,
Yeah,
yes.
oh, yeah, no,
That's why I'm just wondering, are you considering to use large eddy simulation to replace gravity wave parameterization on the Smagorinsky approach 1963?
I'm not sure what you mean. I mean,
Replace of a gravity wave parameterization,
like just replacing it.
but eddy dissipation.
Oh, no, I'm not, no.
You're not considering this, all right?
No, I mean, learn from an LES what to do, maybe. But
Yeah, but LAS at high resolution especially is a natural framework to make basically to resolve instability of resolved gravity wave and large scale flow. And this is might help a lot. And it helps naturally.
Discussion for the brewery. Because I thought there was a couple of more questions. Judith, go ahead.
Thank you. So I'm aware of some work about topography, which is something we normally know, or orography, where they put low resolution topography in high resolution models. And it turns out that there's a lot of interaction between the flow over mountains and their orographic representation. I'm not sure if it plays a big role over the Southern Oceans, but have you considered looking at orography as a source for this? And so some people actually, what they do is in high resolution, in weather forecasting, they represent the uncertainty associated with flow over orography by taking the mountains and moving them a grid point to the right and to the left and the north and the south. And they have extremely good results because it represents that interaction.
interesting. I mean,
I'm not suggesting this.
we've torqued the knobs on the mountain wave scheme a lot. And we haven't been able to fix things in the southern polar vortex. We've also tried, I mean, and this gets at the lateral propagation, we've tried actually smoothing the tendencies from the gravity wave scheme in the dipole. And that would be, some crude representation of lateral propagation. The idea being that if you get things to go into the Drake passage, then somehow you'll solve the problem. And that, was disappointing. I don't know if stochastic variations of topography are going to give us what we need. I just think we need more momentum flux.
So we need to move on to the next speaker, which is also a significant change in the model. It's going to be Danny.
Guys, do you have 20 minutes?
You have 20 minutes.
Yeah, okay. All right, I hope you can hear me well. I'm Danny. I'm a postdoc working at ASP ACOM, also affiliated with UCLA. And I want to thank my co-authors, Jasper Cook, my PhD supervisor, and Simone and Dave from ACOM and CGD, as well as Leon Lei and Natalie, who just presented half an hour ago. So I'm improving the dust emission scheme in a lot of models, like CSM, it's a major one. So I'm developing a new mechanistic scheme that it's trying to represent the old one, to replace the old one. It's essentially a tuning problem, just like all of you are doing here. You see the right-hand side shows you the default ZSM22 simulation of dust aerosol optical depth. And the left-hand side shows you the Modus Aqua data. So they don't really match super well in terms of source regions. You see some blobs over different regions, like especially the southern hemisphere and in South America, South Africa, and Australia. That's not something that we want. And that has a lot of consequences towards radiation simulation, aerosol simulation, also chemistry as well. So, so the goal is to change aerosol distribution in the spatial and temporal variability. And we're trying to use a new dust emission physics to highlight the right source locations, as well as improving the right background conditions for aerosol concentration. So if you look at the ocean concentrations of dust as well, you will see a lot of underestimations over low dust regions, but you'll see at the same time overestimations of the continents compared to the satellite data. So that's something we want to fix. So I have done several things here. First, we took away Sender 2003. We replaced it by a base scheme called Cook 2014. So that's the base scheme that I was working on. And so you see the left column shows you the CTSM5 dust emission. You see that Sender, it's like very spatially discrete, but very high emissions across different parts of the world, but they're too discrete. So it's not very realistic to us. And so you see those blobs in those Chem6 dust AOD spatial distribution that we don't like. And then in Cook 2014, we replaced it with, we took away the soil erodibility map that the Sender used, and we tried to model it just using a pure function of soil moisture. So you'll see this spatial distribution of dust emission. It's more closely following the spatial distribution or the seasonality of soil moisture. And that gives us a sort of mildly, moderately improved dust AOD in Chem6 as well. So that's one of the major improvements. And I just want to say that dust emission, it's a threshold parameterization. So it really depends on how the meteorology is sensitive, how dust emission is sensitive to the meteorology and the parameterization to the threshold. So you see the friction velocity needs to be larger than a threshold value of the friction velocity in order to trigger dust emission. So tuning the threshold value is something that I work a lot on. And then I try to add some processes. So I'm going to talk about two here. The first is the wind drag partition due to surface roughness. So in the dust emission scheme, I consider rocks and vegetation as surface roughness. So there are obstacles that you can see, you know, comparing to nothing on the soil surface to something on top of the soil surface. You see some wind stress partitioned or absorbed or dissipated by the surface obstacles. So if there's a tree over there, then there will be reduction in the wind stress. So we came up with an equation that describes the drag partition or dissipation effects. And so that's a variable called the F effective wind drag partition factor that ranges from 0 to 1. And that sort of just highlights the major dust emission source across the world. So you see the most erodible source regions like the Sahara or the northwestern China will have a value really close to 1. And if you move on to the rainforest or boreal forest, then you see the value goes to 0. So we use that to scale the friction velocity. So that's one of the major work that I've done. The F effective is a function of the roughness of rock as well as the LAI. So it's considering both the vegetation cover and the rock cover across the world. So if you see a friction velocity, that's the CTSM5 output of U star. It has a spatial distribution like so in the lower left graph. Then we'll modify it by multiplying the U star by the F effective to become something like so. Then you see we're really highlighting regions like the Sahara or Australia and those most erodible regions across the world. And we'll use this modified U star to simulate dust emissions instead, and that gives you a much more clean spatial distribution of dust if you even zoom into a regional, let's say if you just look at the Sahara, then it will still give you a much better regional spatial distribution of dust over Africa. So the other thing that I have done is to consider the subtime-step dust emissions due to the high frequency turbulent wind gusts. So it's like a lot of subgrid parameterization that CSM people have done. You know, if you look at the big grid, you don't see any fluxes coming out of that because the mean does not give you a lot of meaningful information. But if you look at the subgrid, then you look at a lot of smaller scale variability that gives you a lot of fluxes coming out. And so the same thing goes to the time. So you see things like the wind speed over the marginal source regions, like North America and South Africa, they will have wind speed regularly lower than the threshold value. But that's only when you are thinking about the mean. If you think about the fluctuation, especially within a time step, there are a lot of spikes, a lot of fluctuations within those time steps that can occasionally trigger dust emissions within that time step. So if you use the mean wind speed, that gives you 0 emission in that time step over those marginal sources. But if you look at those spikes, if you account for the number of spikes within the time step, then that actually triggers a lot of small emissions within the time step. So this is what this algorithm is trying to account for, okay? The mean winds cannot trigger emissions, so there's no emission. So that partially also explains why we have low dust bias over those marginal source regions. But if those turbulent wind gusts can, those wind episodes can, then we need to account for those time step wind gustiness. So that's the problem that I just talked about. We have underestimated dust over marginal source regions, but trying to account for these subtime steps emissions will alleviate that problem. So Francesco Comola 2019 has a statistical description to account for subtime step wind spread for generating emissions for different aerosols, not just dust, but all kinds of aerosols, and just mainly use a similarity theory description. So you see the wind spread instead of the wind mean. The wind spread has a shear contribution and a buoyancy contribution. And we can use a statistical description to account for the number of spikes, the episodes within a time step to actually generate emissions. And that's a lot of math and stats over there. So I'll just leave it to the paper. If you're interested, go to the paper and take a look. But I just want to show you the plots here. If you just look at Cook 2014, that's a dust emissions mostly from the major source regions like the Sahara. But if you look at our new scheme, which is Learn 2023 right now, using the Comola 2019, the C19, then we account for those subtime step dust emissions from semi-arid areas. So you see a lot more emissions coming out of the United States, for example, or Patagonia, the peripheral regions of the major dust desert areas, like the Sahel region has a lot more emissions right now. Or the peripheries of Australia also has a lot more emissions. So that's what we are trying to capture. So subtime step dust emissions due to turbulence. So these are two very interesting developments that we had. And then we are going into the evaluation in CSM22. So the first column shows you Sender, which is the old scheme, and then Learn 2023 in the middle. Hopefully by just looking at the dust AOD, which is the lower row, that sort of convince you that our dust emissions and dust AODs are performing a lot better compared to Zender 2003. If you compare the AOD maps against the Modus Aqua, which is the right plot, lower right plot, then I hope that sort of convinces you that Australia is doing better. Most of the Southern Hemisphere is doing better. Africa is also doing better. And one thing that I think degraded a little bit is China, Northwestern China. The Taklamakan emission has dropped compared to Zender. And that's something that we are trying to fix. I think we need to think about how to fix that issue. I think there could be some problems in the input meteorology, or maybe we just missed some process that we don't know. And I also want to go back to look at the regional dust bias. So I'm showing you the regional evaluation, which is average dust AOD across 15 dust regions that we concern across different seasons. So you see an overall overestimation. So the x-axis is the modeled dust AOD, and the y-axis is the David Ridley regional reanalysis dust AOD. And so that's sort of a golden standard of what we try to follow, try to match the regional dust towards. And you see this regional overall overestimation over the largest, the biggest, the most dustiest areas like the Sahara. So you see the regression slope is generally smaller than 1. So for example, for Sander, it's 0.74, which means you have an overestimation over the dustiest regions and an underestimation over the marginal source regions. But we're trying to also argue that, Learn 2023 is trying to fix that regional bias by promoting more dust from those marginal source regions. But not just that, you'll see that the error is largely reduced. So the R-squared value increased by quite a bit, the root mean square error decreased by quite a bit. And overall, the value just aligned close to the one-to-one line. And the right figure shows you the two reanalysis products. So we have the Modus Aqua dust AOD product and the David Ridley regional dust AOD, and they just match almost perfectly. So good for them. Right. So I just also want to point out that the largest issue is again here. It's this green dot. It's springtime Taklamakan dust emission. It's a serious underestimation by the model, something that we really want to fix. But it will be there for a short while. Tuning in Chem 7, CSM3, I'm showing you some issues that we encountered recently. So dust changed by quite a bit in CSM3, and I try to look into the issues, and mostly comes down to the friction velocity change. A lot of things can cause friction velocity to change, right? Like the boundary layer scheme could cause it to change. The roughness scheme could cause it to change. I try to attribute most of the issues to the switch in the CTSM roughness scheme from Zen Wang to Ronnie Mai 2022. And so you see major reductions of roughness or just friction velocity over the most arid regions like Sahara and the northwestern China. So it's already bad, now it's even worse. Okay, so we have an decrease in the U star over those areas. But at the same time, you have more higher roughness in general over the boreal forests and tropical rainforests. So these changes in the input meteorology will, propagate downstream and then impact on the regional dust biases. So you end up seeing something like this, the Chem 7 dust AOD, with major overestimations over the southern hemisphere and underestimations over the major dust source regions and things like that. So we are trying to fix these issues by so what I was trying to do was to reduce the sensitivity of dust emissions. So originally in the theory, it was allowed that the dust emission flux scales with the U star to the power of 7, which is kind of crazy, right? In Koch's theory, in marginal source regions. Okay, so now we cap it to the power 3, okay, which is still allowed by the theory. So it's, the theory is constructed by using in situ measurements. So it's very small scale. You adjust it to 100 kilometers square grid cell, then you adjust a little bit the sensitivity. I think that's fair enough. So yeah, so hopefully, if the input fields are changed or improve it with CSM updates, then we tweak the equation in the range that the theory allows, okay? So, but I try my best this time to reduce the dust emission sensitivity to the MET fields to save work for the future. So at the end, this is what you will see in CSM3 Chem 7, hopefully. So we tune it back to a reasonable range, showing you, reasonable dust AOD pattern and the dust emission pattern. All right. And we also talked about this a couple of months ago, that LAI has a pretty strong control to dust emission as well. So you see, if we switch from satellite phenology LAI, modus LAI to BGC crop LAI, then you see changes in the leaf area index by quite a bit. I max out the color bar at 1, so you see the arid regions a little better. So you see LAI, the value and the spatial distribution of LAI directly controls the spatial pattern of dust emissions. You see that pretty clearly over America or South America, for example. So that's something that we should be careful about as well. So don't be surprised when you see dust change by a little bit when you switch from an F case to a B case, for example. I guess I'll just quickly wrap up. I'll talk about this more in the land model working group meeting. We just talk about, we use inverse modeling, inverse analysis to show dust increase by 50% from pre-industrial period to the contemporary climate. So you see from the 1850s to the 2000s, you see a 50% increase in the dust emission flux, which is the left-hand side graph. And at the same time, we show that most of the CMIP6 dust emissions were not able to capture that increasing trend. So you see all the dashed lines on the right-hand side, that's all the CMIP6 models. They couldn't capture that historical increase effects. And so we just produce this historical dust emission data set and try to feed it into different CMIP models or Earth system models. So we did an AeroCom experiment on historical dust variability and climate forcing. But you know, eventually what we need to think about is to mechanistically model this variability in the CSM. Is it an issue of land use change or things like that, that we don't couple enough? So I'm going to talk more about this in the LMWG meeting. So take-home message, we changed the dust emission scheme into a more complicated one, but hopefully more accurate. It's available since CTSM 5219, and let me know if you want a CSM 222 sandbox. And you can now switch between dust emission method from Learn 2023 to Center 2003 in Camp 7. And we strongly suggest that we always tune dust to a global mean of 0.03 in the 2000s. That's a pretty good benchmark provided by David Ridley and Colette Hill. And hopefully more developments in the dust cycle modeling coming in the future CSM version. All right, thank you.
Time for a quick question. You're one of the few people with a nameless variable with your last name.
Do people put their first name on it?
You know any other nameless that has his last name in it? So pretty cool.
Richard.
I think you mentioned gustiness, and I'm wondering, how do you define that? I mean, because I think of convective gustiness, dry, I mean, Sahara gustiness, I'm not quite sure.
Yeah, that's how we define it, the similarity theory. So that hopefully sort of captures the shear and the buoyancy variability. That's modeled by CSM and Chem. But that's how we define it. So all the subtimes that affect fluctuations are defined by this spread. That's how we do it.
Right, thank you, Danny. We're running a little behind. All right, last but not least is an online presentation. Will Martina be driving herself, or should I drive the slideshow?
She asked me earlier. Okay. I don't know if she's online, she should get it.
I'll give you the next one. All right. Dynamics.
Martina had something come up this morning, so she asked me to give this talk. I apologize. I'll be seeing the slides, not exactly for the first time, but I'll. All right. So the motivation of this study is to try to get at the impacts of model top height and vertical resolution in our model. Previously, before CAM 7, we had the situation depicted here. That is WACCM in the solid dots and CAM in the open circles really had, they overlapped in the troposphere basically and nowhere else. We've recently moved to this this selection of vertical grids. Here in red is the CAM mid-top model, 93 levels. In black is the 135 level WACCM configuration, which, as you can see, not only has a higher top, but it also has substantially higher resolution through most of the stratosphere. So again, we're kind of in the situation where WACCM and CAM don't really quite agree. So we wanted to develop a new, we developed a new grid that will allow us to make comparisons more directly, and that's indicated by that L120 line. So this third grid that I'll be talking about in this talk is the WACCM grid, basically just, with the top lopped off at about 80 kilometers. So that is the same lid, the same model top height as CAM MT, and it has the same sort of increased vertical resolution that the WACCM grid has in the stratosphere. So, I mean, you can think about the the L120 versus L135 as, being a rigorous test of model top height sensitivity. And you can think of L120 versus L93 as testing the sensitivity of this extra resolution in the stratosphere. So just as a shorthand. So this is the motivation here. We want to determine where model top is important and where vertical resolution in the stratosphere is important. So this is the setup of the experiments that Martina performed. They're 18.5 years long. And the vertical grids are as described in the last slide. And no tuning was done for no configuration specific tuning was done. All the parameters in the all the physics parameters, gravity waves, etc., are the same in all the runs. And just these runs do not include the moving mountain scheme. So first, we look at the impact on the QBO, and there's, I would say, not much to talk about. I was a little surprised that there wasn't more difference between L93 and the higher resolution in L120 and L135, but it seems, generally speaking, the QBO, below about 30 kilometers altitude is very similar in all three configurations. As you go higher, it looks like differences start to set in. But in the stratosphere, all the way down to the tropopause, lower stratosphere all the way down to the tropopause, the QBO looks pretty similar in all of the runs. I'm not going to say much about this because I don't understand this analysis very well. But one thing you can see on the right side is a plot of QBO amplitude. And again, there you see that, you know, the dark blue, light blue, and orange lines are the three configurations. And none of the three agree very well, or, you know, there's room for improvement compared to ERA, but between the three configurations, there's not much difference. This is the so-called water vapor tape recorder. This is just a seasonal cycle of water vapor right above the tropopause. And, you know, the water vapor at the tropopause is modulated by the temperature of the tropopause, which goes up and down. So water vapor saturates and leads to kind of a signal that you can track in time that moves up from the tropopause lofted by the meridional circulation in the lower stratosphere. Again, Martina has put here that the WACCM L135 is a little better. I guess I can see that. It's a little wetter. But overall, I'd say the differences here are kind of, you know, they're second order. So again, for this lower stratospheric process, all three configurations, I'd say, you know, agree fairly well. This is now zonal mean zonal wind for DJF, northern winter. And I was actually surprised here. There are more differences than I expect. You know, there's a lot of variability in the northern hemisphere. So maybe 18 years is not long enough. But at any rate, here in this set of runs, you do see what might be an impact of model top. L120 and L93 look fairly similar, at least in the winter hemisphere, whereas L135, you know, does start to deviate a little bit. In the southern hemisphere, winter, I'd say there's less difference overall between the three configurations. Certainly, it's hard. It's hard to do a difference plot in your head, but it looks to me like, you know, if you look almost anywhere in the vertical here, the three configurations are very close. So here again in the, you know, even up through the mesosphere, lower mesosphere at least, down through the stratosphere, the three vertical grids don't show a lot of difference. Of course, we're not looking, you know, we're not looking into the mesosphere where L93 and L120 don't have any grid points. So this is only, you know, we're focusing on the impact of these three grids on stratospheric circulations. So here is here's the impact of model top on the polar. I'm going to have to confess, I'm not exactly sure. These look like differences between 135 and 120, not with observation. So I guess this is showing us that there are, you know, there are some differences between the 135 level configuration and the 120 level configuration down into the, you know, down into the stratosphere. These are biases with respect to ERA, and, you know, not surprisingly, they're especially in the southern hemisphere, which is on the on the right side, 60 south. They're very large. And again, I think, as I pointed out before, these runs don't incorporate moving mountain schemes, so we expect the vortex to be quite a bit stronger than it is in ERA 5. So this is seasonal cycle. This is a time series of daily wind, daily zonal mean wind at 60 north and 10 hectopascal. You know, the solid lines are the means over many years, and the shading or the envelopes are well, they show the envelope over the 18 years of the simulation. And again here, I think the take home is that for this diagnostic at 10 hectopascal, there's nothing obvious, no obvious systematic difference between the three vertical grid configurations. Here's a distribution of sudden stratospheric warmings. I'm just going to leave this up and not comment on it. 18 years may not be long enough to get a good characterization of the sudden stratospheric warming climatology, but there are some interesting differences here, I gotta say. But yeah, I'm not going to comment anymore. We'll have to look into this. So this is EP flux divergence, the force on the resolved force on the atmosphere. Again, you know, I think they're not differences that, you know, they're not alarming differences between the configurations in the stratosphere at any rate. Okay, same plot for southern winter. And I'm going to skip these plots because I have to confess, I'm not quite sure yet what they're showing, but they're in the PowerPoint if people want to look at them later. So I'll just I'll go through her conclusions now. I think the bottom line for us here is that this set of 3 runs doesn't reveal any large differences in the simulation below the stratopause. So somewhat surprisingly to me, even the increased vertical resolution that the WACCM grid has doesn't seem to have a huge impact on the simulated climate in the stratosphere. And the model top difference between WACCM and MT doesn't have an impact on the stratospheric circulation. So I think this is really getting at the survey that the WACCM people have sent out on interest in the community. I think this analysis does suggest that MT is reasonable to use for stratospheric, you know, for stratospheric studies. And I'm going to stop there and try to take any questions if there are any questions.
Yeah, so this was done without the moving mountain. So we have large biases in the polar region.
Right.
And you could, I mean, if we would fix it, I mean, we can fix it with the moving mountain. it could be that we see maybe larger differences.
Could be.
Because of this really large bias, maybe things don't show up. So is there a plan to redo those?
I would like to redo this, every time we have kind of a reasonably stable version, I think we should look at the impact of the model top and vertical resolution. Yeah, so we will redo this with the latest gravity waves.
Yeah.
Judith?
I have a question that you can answer. So it's a bit deviating from the talk, but so I, especially in perspective of Meg's talk today about the impact of ZM on ENSO or of this gustiness parameterization on ENSO, have you looked, or what are the differences of the CM scheme in CAM 6 versus CAM 7? And have you looked at the impact of running the same CM scheme in the high top with the new additional vertical levels or not? Does it change the intermittency of how the CM scheme gets triggered? Is that something somebody has looked at?
So the problem with running the ZM scheme as it was in CAM 6 with increased resolution in the boundary layer is that it generates kind of pathological looking tendencies near the surface. There have been studies that looked at kind of a fourth grid, which has the same top and vertical resolution in the stratosphere as L93. And I'm not sure the L83 configuration. I'm not sure what those have shown. But what are you getting at with the question?
I was trying to understand which effect the additional layers have on the ZM scheme by itself, without any other changes.
It's hard to say. I think the ZM scheme, we can use the new ZM scheme with coarser vertical resolution. Then it doesn't seem to, I don't know if Rich is here anymore, but
Yeah, I can ask Rich.
I believe we could say that with the old scheme, with coarse vertical resolution using the new scheme, the answers look a lot like they looked with ZM1 and coarse vertical resolution.
Thank you.
Just quick suggestion. I don't see the temperature comparison for this stock. So perhaps it would be very interesting to compare 120 levels versus 93 levels of temperature. Because especially also with vacuum, because you have different basically radiation schemes.
Yeah. That's a good suggestion.
Right. Oh, last question, Dave?
It's not a question, it's a comment. We had a meeting today earlier with the WACCM team and the WACCM working group. And I think the idea is that Martina is going to write a paper that's going to summarize all this when we get to the final version and really try to provide guidance to the community about, the usefulness of MP versus WACCM X.
Right.
Presuming, and asking the same question about this vertical resolution. Right. So that'll probably, come out with a CSM series of papers. So it's like in the plans.
Right. Thanks.
Can I get a quick show of hands of who plans to go to Southern Sun now? Get an idea. Okay, thank you. All right, see everybody tomorrow.